Hi, welcome to the first section of the course, Getting Started with Parallel Computing in Python. In this section, we'll deal with parallel computing and its memory architecture. We'll also look at memory organization and parallel programming models. Next, we'll see how to design a parallel program and also to evaluate the performance of a parallel program. Further, we'll get introduced to Python, and we'll work with the processes and thread along with it. So let's begin with the first video of this section, the parallel computing memory architecture. In this video, we'll learn about Flynn's taxonomy, which includes SISD, MISD, SIMD, and MIMD. We'll now take a look at the parallel computing memory architecture. Based on the number of instructions and data that can be processed simultaneously, computer systems are classified into four categories. 1. Single instruction, single data, SISD. 2. Single instruction, multiple data, SIMD. 3. Multiple instruction, single data, MISD. 4. Multiple instruction, multiple data, MIMD. This classification is known as Flynn's taxonomy. Let's understand what SISD is. The SISD computing system is a uniprocessor machine. It executes a single instruction that operates on a single data stream. In SISD, machine instructions are processed sequentially. In a clock cycle, the CPU executes the operations which are 1. Fetch. The CPU fetches the data and instructions from a memory area which is called a register. 2. Decode. The CPU decodes the instructions. 3. Execute. The instruction is carried out on the data. The results of the operation is stored in another register. Once the execution stage is complete, the CPU sets itself to begin another CPU cycle. This is how the SISD architecture schema works. The algorithms that run on these type of computers are sequential, or serial, since they do not contain any parallelism. Examples of SISD computers are hardware systems with a single CPU. The main elements of these architectures, also known as von Neumann architectures, are as shown. 1. Central memory unit. This is used to store both instructions and program data. 2. CPU. This is used to get the instruction and/or data from the memory unit, which decodes the instructions and sequentially implements them. 3. The I/O system. This refers to the input data and output data of the program. The conventional single processor computers are classified as SISD systems. This figure specifically shows which areas of a CPU are used in the stages of fetch, decode, and execute. Now let's see what MISD is. In this model, N processors, each with their own control unit, share a single memory unit. In each clock cycle, the data received from the memory is processed by all processors simultaneously, each in accordance with the instructions received from its control unit. In this case, the parallelism, instruction level parallelism, is obtained by performing several operations on the same piece of data. The types of problems that can be solved efficiently in these architectures are rather special, such as those regarding data encryption. For this reason, the computer MISD did not find space in the commercial sector. MISD computers are more of an intellectual exercise than a practical configuration. This is how the MISD architecture scheme looks. Next, we'll take a look at SIMD. An SIMD computer consists of N identical processors, each with its own local memory, where it's possible to store data. All processors work under the control of a single instruction stream. In addition to this, there are N data streams, one for each processor. The processors work simultaneously on each step and execute the same instruction, but on different data elements. This is an example of data-level parallelism. The SIMD architectures are much more versatile than MISD architectures. Numerous problems covering a wide range of applications can be solved by parallel algorithms on SIMD computers. Another interesting feature is that the algorithms for these computers are relatively easy to design, analyze, and implement. The limit is that only the problems that can be divided into a number of subproblems, which are all identical, each of which will then be solved contemporaneously through the same set of instructions, can be addressed with the SIMD computer. With the supercomputer developed according to this paradigm, we must mention the Connection Machine, 1985 Thinking Machine, and MPP, which is NASA from 1983. As we'll see in Section 6, GPU Programming with Python, the advent of Modern Graphics Processor Unit, or GPU, built with many SIMD embedded units has led to a more widespread use of this computational paradigm. We now move on to understand what MIMD is. This class of parallel computers is the most general and more powerful class according to Flynn's classification. There are N processors, N instruction streams, and N data streams in this. Each processor has its own control unit and local memory, which makes MIMD architectures more computationally powerful than those used in SIMD. Each processor operates under the control of a flow of instructions issued by its own control unit. Therefore, the processors can potentially run different programs on different data, solving subproblems that are different and can be part of a single larger problem. In MIMD, the architecture is achieved with the help of the parallelism level with threads and/or processes. This also means that the processors usually operate asynchronously. The computers in this class are used to solve those problems that do not have a regular structure that is required by the model SIMD. Nowadays, this architecture is applied to many PCs, supercomputers, and computer networks. However, there is a counter that you need to consider. Asynchronous algorithms are difficult to design, analyze, and implement. Great! So now we know how the parallel computing memory architecture works. In the next video, we'll take a look at memory organization. In the previous video, we took a closer look at the parallel computing memory architecture. In this video, we'll learn in depth about the shared memory. So now we'll take a look at the memory organization. Another aspect that we need to consider to evaluate a parallel architecture is memory organization, or rather the way in which the data is accessed. No matter how fast the processing unit is, if the memory cannot maintain and provide instructions and data at a sufficient speed, there will be no improvement in performance. The main problem that must be overcome to make the response time of the memory compatible with the speed of the processor is the memory cycle time, which is defined as the time that has elapsed between two successive operations. The cycle time of a processor is typically much shorter than the cycle time of the memory. When the processor starts transferring data to or from the memory will remain occupied for the entire time of the memory cycle. During this period, no other device, I/O controller, processor, or even the processor itself that made the request can use the memory because it will be committed to respond to the request. This is the graphical representation of the memory organization in MIMD architecture. Solutions to the problem of access memory resulted in a dichotomy of MIMD architectures, as shown in the figure. In the first type of system, known as the shared memory system, there is high virtual memory and all processors have equal access to data and instructions in this memory. The other type of system is the distributed memory model, wherein each processor has a local memory that is not accessible to other processors. The difference between shared memory and distributed memory lies in the structure of the virtual memory or the memory from the perspective of the processor. Physically, almost every system memory is divided into distinct components that are independently accessible. What distinguishes a shared memory from a distributed memory is the memory access management by the processing unit. If a processor were to execute the instruction load ROI, which means load in the RO register of the contents of the memory location I, the question now is what should happen? In a system with shared memory, the I index is a global address and the memory location I is the same for each processor. If two processors were to perform this instruction at the same time, they would load the same information in their registers RO. In a distributed memory system, I is a local address. If two processors were to load the statement RO at the same time, different values may end up in the respective registers RO, since, in this case, the memory cells are allotted one for each local memory. The distinction between shared memory and distributed memory is very important for programmers because it determines the way in which different parts of a parallel program must communicate. In a system, shared memory is sufficient to build a data structure in memory and go to the parallel subroutine, which are the reference variables of this data structure. Moreover, a distributed memory machine must make copies of shared data in each local memory. The copies are created by sending a message containing the data to be shared from one processor to another. A drawback of this memory organization is that sometimes these messages can be very large and take a relatively long transfer time. We'll now take a closer look at shared memory. The schema of a shared memory multiprocessor system is shown here. The physical connections here are quite simple. The bus structure allows an arbitrary number of devices that share the same channel. The bus protocols were originally designed to allow a single processor and one or more disks or tape controllers to communicate through the shared memory here. Note that each processor has been associated with a cache memory, as it is assumed that the probability of a processor needs data or instructions present in the local memory is very high. The problem occurs when a processor modifies data stored in the memory system that is simultaneously used by other processors. The new value will pass from the processor cache that has been changed to shared memory. Later, however, it must be also passed to all other processors so that they do not work with obsolete value. This problem is known as the problem of cache coherency, a special case of the problem of memory consistency, which requires hardware implementations that can handle concurrency issues and synchronization similar to those having thread programming. The main features of shared memory systems are: 1. The memory is all the same for all processors. For example, all the processors associated with the same data structure will work with the same logical memory addresses, thus accessing the same memory locations. 2. The synchronization is made possible by controlling the access of processors to the shared memory. In fact, only one processor at a time can have access to the memory resources. 3. A shared memory location must not be changed from a task while another task accesses it. 4. Sharing data is fast. The time required for the communication between two tasks is equal to the time for reading a single memory location. It is depending on the speed of memory access. The memory access in shared memory systems are as follows. 1. Uniform memory access, or UMA. The fundamental characteristic of this system is the access time to the memory that is constant for each processor and for any area of memory. For this reason, these systems are also called symmetric multiprocessor. They are relatively simple to implement, but not very scalable. The programmer is responsible for the management of the synchronization by inserting appropriate controls, semaphores, locks, and so on in the program that manages resources. 2. Non-uniform memory access, or NUMA. These architectures divide the memory area into a high-speed access area that is assigned to each processor and a common area for the data exchange with slower access. These systems are also called Distributed Shared Memory Systems, or DSM. They are very scalable but complex to develop. 3. No Remote Memory Access, or NORMA. The memory is physically distributed among the processors, or local memory. All local memories are private and can only access the local processor. The communication between the processors is through a communication protocol used for exchange of messages, the Message Passing Protocol. 4. Cache-only memory access, or COMA. These systems are equipped with only cache memories. While analyzing NUMA architectures, it was noticed that these architectures kept the local copies of the data in the cache, and that these data were stored as duplication in the main memory. This architecture removes duplicates and keeps only the cache memories. The memory is physically distributed among the processors, or local memory. All local memories are private and can only access the local processor. The communication between the processors is through a communication protocol for exchange of messages, the Message Passing Protocol. Awesome! So in this video we learned about shared memory in detail. Our next video will be the continuation of this one, where we will take a look at distributed memory. In the previous video we learned about shared memory. In this video we'll take a closer look at distributed memory. In a system with distributed memory, the memory is associated with each processor, and a processor is only able to address its own memory. Some authors refer to this type of system as multi-computer, reflecting the fact that the elements of the system are themselves small, complete systems of a processor and memory, as you can see in this figure. This kind of organization has several advantages. At first, there are no conflicts at the level of the communication bus or switch. Each processor can use the full bandwidth of their own local memory without any interference from other processors. Secondly, the lack of a common bus means that there is no intrinsic limit to the number of processors. The size of the system is only limited by the network used to connect the processors. Thirdly, there are no problems of cache coherency. Each processor is responsible for its own data and does not have to worry about upgrading any copies. The main disadvantage is that the communication between processors is more difficult to implement. If a processor requires data in the memory of another processor, the two processors should necessarily exchange messages via the Message Passing Protocol. This introduces two sources of slowdown. To build and send a message from one processor to another takes time, and also any processor should be stopped in order to manage the messages received from other processors. A program designed to work on a distributed memory machine must be organized as a set of independent tasks that communicate via messages. This is how the basic message passing works. The main features of distributed memory systems are: 1. Memory is physically distributed between processors. Each local memory is directly accessible only by its processor. 2. Synchronization is achieved by moving data, even if it's just the message itself, between processors. Communication. 3. The subdivision of data in the local memories affects the performance of the machine. It's essential to make a subdivision accurate so as to minimize the communication between the CPUs. In addition to this, the processor that coordinates these operations of decomposition and composition must effectively communicate with the processors that operate on the individual parts of data structures. 4. The message passing protocol is used so that the CPUs can communicate with each other through the exchange of data packets. The messages are discrete units of information in the sense that they have a well-defined identity, so it's always possible to distinguish them from each other. We'll now take a look at massive parallel processing. MPP machines are composed of hundreds of processors, which can be as large as hundreds of thousands in some machines, that are connected by a communication network. The fastest computers in the world are based on these architectures. Some example systems of these architectures are Earth Simulator, Blue Gene, ASCI White, ASCI Red, and ASCI Purple and Red Storm. So what do we mean by a cluster of workstations? These processing systems are based on classical computers that are connected by communication networks. The computational clusters fall into this classification. Here's an example of a cluster of workstation architecture. In a cluster architecture, we define a node as a single computing unit that takes part in the cluster. For the user, the cluster is fully transparent. All the hardware and software complexity is masked, and data and applications are made accessible as if they were all from a single node. Here, we've identified 3 types of clusters. 1. The failover cluster. In this, the node's activity is continuously monitored, and when one stops working, another machine takes over the charge of those activities. The aim is to ensure a continuous service due to the redundancy of the architecture. 2. The load balancing cluster. In this system, a job request is sent to the node that has less activity. This ensures that less time is taken to complete the process. 3. The high-performance computing cluster. In this, each node is configured to provide extremely high performance. The process is also divided in multiple jobs on multiple nodes. The jobs are parallelized and will be distributed to different machines. Let's look at the heterogeneous architecture. The introduction of GPU accelerators in the homogeneous world of supercomputing has changed the nature of how supercomputers were both used and programmed previously. Despite the high performance offered by GPUs, they cannot be considered as an autonomous processing unit, as they should always be accompanied by a combination of CPUs. The programming paradigm, therefore, is very simple. The CPU takes control and computes in a serial manner, assigning to the graphic accelerator the tasks that are computationally very expensive and have a high degree of parallelism. The communication between CPU and GPU can take place not only through the use of a high-speed bus, but also through the sharing of a single area of memory for both physical or virtual. In fact, in the case where both the devices are not equipped with their own memory areas, it is possible to refer to a common memory area using the software libraries provided by the various programming methods, such as CUDA and OpenCL. These architectures are called heterogeneous architectures, wherein applications can create data structures in a single address space and send a job to the device hardware appropriate for the resolution of the task. Several processing tasks can operate safely on the same regions to avoid data consistency problems, thanks to the atomic operations. So, despite the fact that the CPU and GPU do not seem to work efficiently together, with the use of this new architecture, we can optimize their interaction with and performance of parallel applications. Excellent! We just learned about distributed memory systems in detail. In the next one, we'll learn about parallel programming models. Previously, we studied the distributed memory system. In this video, we'll take a look at the parallel programming methods, which are 1. The shared memory model. 2. The multi-thread model. 3. The distributed memory message passing model. And 4. The data parallel model. Parallel programming models exist as an abstraction of hardware and memory architectures. In fact, these models are not specific and don't refer to particular types of machines or memory architectures. They can only be implemented, at least theoretically, on any kind of machines. Compared to the previous subdivisions, these programming models are made at a higher level and represent the way in which the software must be implemented to perform a parallel computation. Each model has its own way of sharing information with other processors in order to access memory and divide the work. There is no better programming model in absolute terms. The best one to apply will depend very much on the problem that a programmer should address and resolve. The most widely used models for parallel programming are 1. The shared memory model. 2. The multi-thread model. 3. The distributed memory message passing model. 4. The data parallel model. In this video, we'll give you an overview of these models. A more accurate description will be in the next chapters that will introduce you to the appropriate Python module that implements these. Let's take a look at the shared memory model. In this model, the tasks share a single shared memory area where the access, reading and writing data, to shared resources is asynchronous. There are mechanisms that allow the programmer to control the access to the shared memory, for example, locks or semaphores. This model offers the advantage that the programmer does not have to clarify the communication between tasks. An important disadvantage in terms of performance is that it becomes more difficult to understand and manage data locality. Keeping data local to the processor that works on it conserves memory accesses, cache refreshes, and bus traffic that occur when multiple processors use the same data. Next, we move on to the multi-thread model. In this model, a process can have multiple flows of execution. For example, a sequential part is created, and subsequently, a series of tasks are created that can be executed parallelly. Usually, this type of model is used on shared memory architectures. So it'll be very important for us to manage the synchronization between threads as they operate on shared memory, and the programmer must prevent multiple threads from updating the same locations at the same time. The current generation CPUs are multi-threaded in software and hardware. POSIX threads are the classic example of the implementation of multi-threading on software. The Intel hyper-threading technology implements multi-threading on hardware by switching between two threads when one is stalled or waiting on I/O. Parallelism can be achieved from this model even if the data alignment is nonlinear. We'll now see what a message passing model is. The message passing model is usually applied in the case where each processor has its own memory, or distributed memory systems. More tasks can reside on the same physical machine or on an arbitrary number of machines. The programmer is responsible for determining the parallelism and data exchange that occurs through the messages. The implementation of this parallel program model requires the usage of ad hoc software libraries to be used within the code. Numerous implementations of message passing model were created. Some of the examples are available since the 1980s, but only from the mid-90s was created to standardized model, coming to a de facto standard called MPI, or the Message Passing Interface. The MPI model is designed clearly with a distributed memory, but being models of parallel programming, multi-platform can also be used with a shared memory machine. So what is the data parallel model? In this model, we have more tasks that operate on the same data structure, but each task operates on a different portion of data. In the shared memory architecture, all tasks have access to data through shared memory and distributed memory architectures, where the data structure is divided and resides in the local memory of each task. To implement this model, a programmer must develop a program that specifies the distribution and alignment of data. The current generation GPUs operates high throughout with the data aligned. So this video explained the parallel programming models in detail. Our next video will show us how to design a parallel program. In the previous video, we dealt with parallel programming models. In this video, we'll be designing a parallel program, and for that we'll be carrying out 1. Task decomposition. 2. Task assignment. 3. Agglomeration. 4. Mapping. The design of algorithms that exploit parallelism is based on a series of operations, which must necessarily be carried out for the program to perform the job correctly without producing partial or erroneous results. We'll now take a look at the macro operations that must be carried out for correct parallelization of an algorithm. So the first one is the task decomposition. In the first phase, the software program is split into tasks or a set of instructions that can then be executed on different processors to implement parallelism. To do this subdivision, there are two methods that are used. 1. Domain decomposition. Here, the data of the problems is decomposed. The application is common to all the processors that work on a different portion of data. This methodology is used when we have a large amount of data that we must process. 2. Functional decomposition. In this case, the problem is split into tasks, where each task will perform a particular operation on all the available data. The second one is the task assignment. In this step, the mechanism by which the task will be distributed among the various processes is specified. This phase is very important because it establishes the distribution of workload among the various processors. The load balance is crucial here. In fact, all processors must work with continuity, avoiding an idle state for a long time. To perform this, the programmer takes into account the possible heterogeneity of the system that tries to assign more tasks to better performing processors. Finally, for greater efficiency of parallelization, it's necessary to limit communication as much as possible between processors, as they are often the source of slowdowns and consumption of resources. Next one is agglomeration. Agglomeration is the process of combining smaller tasks with larger ones in order to improve performance. If the previous two stages of the design process partition the problem into a number of tasks that greatly exceed the number of processors available, and if the computer is not specifically designed to handle a huge number of small tasks, some architectures, some as GPUs, handle this fine and indeed benefit from running millions or even billions of tasks, then the design can turn out to be highly inefficient. Commonly, this is because the tasks have to be communicated to the processor or thread so that they compute the said task. Most communication has costs that are not only proportional with the amount of data transferred, but also incur a fixed cost for every communication operation, such as the latency which is inherent in setting up a TCP connection. If the tasks are too small, this fixed cost can easily make the design inefficient. The last one is mapping. In the mapping stage of the parallel algorithm design process, we specify where each task is to be executed. The goal is to minimize the total execution time. Here, you must often make trade-offs, as the two main strategies often conflict with each other. 1. The tasks that communicate frequently should be placed in the same processor to increase locality. And 2. The tasks that can be executed concurrently should be placed in different processors to enhance concurrency. This is known as the mapping problem, and is known to be NP-complete. As such, no polynomial time solutions to the problem in the general case exist. For tasks of equal size and tasks with easily identified communication patterns, the mapping is straightforward. We can also perform agglomeration here to combine tasks that map to the same processor. However, if the tasks have communication patterns that are hard to predict or the amount of work varies per task, it's hard to design an efficient mapping and agglomeration scheme. For these types of problems, load balancing algorithms can be used to identify agglomeration and mapping strategies during runtime. The hardest problems are those in which the amount of communication or the number of tasks changes during the execution of the program. For these kinds of problems, dynamic load balancing algorithms can be used, which run periodically during the execution. We'll now take a look at dynamic mapping. There exists many load balancing algorithms for various problems, both global and local. Global algorithms require global knowledge of the computation being performed, which often adds a lot of overhead. Local algorithms rely only on information that is local to the task in question, which reduces overhead compared to global algorithms, but are usually worse at finding optimal agglomeration and mapping. However, the reduced overhead may reduce the execution time even though the mapping is worse by itself. If the tasks rarely communicate other than at the start and the end of the execution, a task scheduling algorithm is often used that simply maps tasks to processors as they become idle. In a task scheduling algorithm, a task pool is maintained. Tasks are placed in this pool and are taken from it by workers. There are three common approaches in dynamic mapping model. The first one is manager-worker. This is the basic dynamic mapping scheme in which all the workers connect to a centralized manager. The manager repeatedly sends tasks to the workers and collects the results. This strategy is probably the best for a relatively small number of processors. The basic strategy can be improved by fetching tasks in advance so that the communication and computation overlap each other. The second one is hierarchical manager-worker. This is the variant of a manager-worker that has a semi-distributed layout. Workers are split into groups, each with their own manager. These group managers communicate with a central manager, and possibly among themselves as well, while workers request tasks from the group managers. This spreads the load among several managers, and can, as such, handle a larger amount of processors if all the workers request tasks from the same manager. The third and the last one is decentralize. In this scheme, everything is decentralized. Each processor maintains its own task pool and communicates with the other processors in order to request tasks. How the processors choose other processors to request tasks varies and is determined on the basis of the problem. Great! So now we know how to design a parallel program. In the next video, we'll evaluate the performance of the parallel program which was created. In the previous video, we saw how to design a parallel program. In this video, we'll evaluate the performance of a parallel program. For that, we will introduce few performance indexes, such as speed up, efficiency, and scaling. We'll also take a look at Amdahl's law and Gustafson's law. So let's see how to evaluate the performance of a parallel program. The development of parallel programming created the need of performance metrics and a software tool to evaluate the performance of a parallel algorithm in order to decide whether its use is convenient or not. Indeed, the focus of parallel computing is to solve large problems in a relatively short time. The factors that contribute to the achievement of this objective are, for example, the type of hardware used, the degree of parallelism of the problem, and which parallel programming model is adopted. To facilitate this, analysis of basic concepts was introduced, which compares the parallel algorithm obtained from the original sequence. The performance is achieved by analyzing and quantifying the number of threads and/or the number of processes used. To analyze this, a few performance indexes are introduced. The first one is speedup. Speedup is the measure that displays the benefit of solving a problem in parallel. It's defined as the ratio of the time taken to solve a problem on a single processing element, TS, to the time required to solve the same problem on P identical processing elements, TP. We denote speedup by this formula. We have a linear speedup, where if S equals P, it means that the speed of execution increases with the number of processors. Of course, this is an ideal case. While the speedup is absolute when TS is the execution time of the best sequential algorithm, the speedup is relative when TS is the execution time of the parallel algorithm for a single processor. Let's recap these conditions. 1. S is equal to P is linear or ideal speedup. 2. S less than P is real speedup. 3. S greater than P is superlinear speedup. Now let's take a look at the second performance index, which is efficiency. In an ideal world, a parallel system with P processing elements can give us a speedup equal to P. However, this is very rarely achieved. Usually, some time is wasted in either idling or communication. Efficiency is a performance metric estimating how well utilized the processors are solving a task, compared to how much effort is wasted in communication and synchronization. We denote it by E and can define it as shown here. The algorithms with linear speedup have the value of E equals 1. In other cases, the value of E is less than 1. The three cases are identified, which are 1. When E is equal to 1, it's a linear case. 2. When E is less than 1, it is a real case. 3. This condition shows that it's a problem that is parallelizable with low efficiency. We'll now learn about scaling, which is the last performance index. Scaling is defined as the ability to be efficient on a parallel machine. It identifies the computing power, or speed of execution, in proportion with the number of processors. By increasing the size of the problem, and at the same time the number of processors, there'll be no loss in terms of performance. The scalable system, depending on the increments of the different factors, may maintain the same efficiency or improve it. We'll now take a look at Amdahl's law. Amdahl's law is a widely used law used to design processors and parallel algorithms. It states that the maximum speedup that can be achieved is limited by the serial component of the program as shown here, where 1 minus P denotes the serial component, not parallelized, of a program. This means that for, as an example, a program in which 90% of the code can be made parallel, but 10% must remain serial, the maximum achievable speedup is 9, even for an infinite number of processors. Next, we'll take the Gustafson's law. Gustafson's law is based on the considerations which are 1. While increasing the dimensions of a problem, its sequential parts remain constant. 2. While increasing the number of processors, the work required on each of them still remains the same. This states that S times P equals P minus alpha bracket P minus 1, where P is the number of processors, S is the speedup, and alpha is the non-parallelizable fraction of any parallel processors. This is in contrast to Amdahl's law, which takes the single process execution time to be the fixed quantity and compares it to a shrinking per process parallel execution time. Thus, Amdahl's law is based on the assumption of a fixed problem size. It assumes that the overall workload of a program does not change with respect to the machine size, that is, the number of processors. Gustafson's law addresses the deficiency of Amdahl's law, which does not take into account the total number of computing resources involved in solving a task. It suggests that the best way to set the time allowed for the solution of a parallel problem is to consider all the computing resources, and on the basis of this information, it fixes the problem. Brilliant! So here we've learned how to evaluate the performance of a parallel program. In the next video, we'll introduce Python and understand its importance in parallel world. In the previous video, we saw how to evaluate the performance of a parallel program. This video will get us introduced to Python and helps us understand its importance in parallel world. Python is a powerful, dynamic, and interpreted programming language that is used in a wide variety of applications. Some of its features include 1. A clear and readable syntax. 2. A very extensive standard library where through additional software modules we can add data types, functions, and objects. 3. Easy to learn, rapid development, and debugging. The development of Python code in Python can be up to 10 times faster than the C or C++ code. 4. Exception-based error handling. 5. A strong introspection functionality. 6. Richness of documentation and software community. Python can be seen as a glue language. Using Python, better applications can be developed because different kinds of programmers can work together on a project. For example, when building a scientific application, C or C++ programmers can implement efficient numerical algorithms, while scientists on the same project can write Python programs that test and use those algorithms. Scientists don't have to learn a low-level programming language, and a C or C++ programmer doesn't need to understand the science involved. You can read more about it from this link. Python can be downloaded from this website link. Although you can create Python programs with Notepad or TextEdit, you'll notice that it's much easier to read and write code using an Integrated Development Environment, or IDE. There are many IDEs that are designated specifically for Python, including IDLE, for which you can find more information on this link. The other one is PyCharm, and you can visit this link for more information. Next is Sublime Text, for which you can visit this link. The final one is Anaconda, which we have used here. You can find it at this link. Let's take a look at some examples of the very basic code to get an idea of the features of Python. First is the operations with integers. Now open your command prompt and type Python. You can see the Python version and the Anaconda version. Here you can enter this code for operations with integers. Enter the width, then height. Next we will multiply width with height. Remember that this symbol denotes the Python shell. This is how the code appears in the Python shell. Let's see the other basic examples. We'll take a look at complex numbers. Type this code for the complex numbers in the command prompt. As you can see, we have stored the complex number in the value a. In order to find the real number, we enter this code. Next, to find the imaginary value, we type this code. To find the square root, we type this code. Next, try strings manipulation. This is the code for strings manipulation. Store the string in Word as shown. Here's the code for defining lists. To see the first word, type this. To see the last word, type this. To see the second last word, enter this. To see the first and last word, type this. To find the length, this is the code. This is the code for the while loop. For the if command, first we use the input parenthesis statement to insert an integer in the code shown. Then we implement the if condition on the number inserted using these lines of code. For the loop code, looks like this. Next, you can see the code for defining functions. Here's the code for importing modules. We will define classes using the code shown here. We'll now take a look at Python in parallel world. To be an interpreted language, Python is fast, and if speed is critical, it easily interfaces with extensions written in faster languages, such as C or C++. A common way of using Python is to use it for the high-level logic of a program. The Python interpreter is written in C and is known as CPython. The interpreter translates the Python code in an intermediate language called Python bytecode. which is analogous to an assembly language, but contains a high level of instruction. While a Python program runs, the so-called evaluation loop translates Python bytecode into machine-specific operations. The use of interpreter has advantages in code programming and debugging, but the speed of a program could be a problem. A first solution is provided by third-party packages, where a programmer writes a C module and then imports it from Python. Another solution is the use of a just-in-time Python compiler, which is an alternative to CPython. For example, the PyPy implementation optimizes code generation and the speed of a Python program. In this course, we'll examine a third approach to the problem. In fact, Python provides ad hoc modules that could benefit from parallelism. The description of many of these modules in which the parallel programming paradigm falls will be discussed in subsequent sections. However, in this section, we'll introduce the two fundamental concepts of threads and processes and how they are addressed in the Python programming language. So, in this video, we introduced Python and saw its importance in parallel world. In the next video, we'll start working with processes in Python. In the previous video, we introduced Python. This video will get us introduced to the processes in Python and help us to start working with them. So let's get started. A process is an executing instance of an application. For example, double-clicking on the internet browser icon on the desktop will start a process that runs the browser. A process can consist of multiple parallel threads. Starting the browser, the operating system creates a process and begins executing the primary threads of that process. Now we'll check how the Python programming language works with processes. On common operating systems, each program runs in its own process. Usually, we start a program by double-clicking on the icon's program or selecting it from a menu. In this video, we simply demonstrate how to start a single new program from inside a Python program. A process has its own space address, data stack, and other auxiliary data to keep track of the execution. The OS manages the execution of all processes, managing the access to the computational resources of the system via a scheduling procedure. In the first Python application, you'll simply get the Python language installed. Refer to this link to get the latest version of Python. To execute this first example, we need to type these two programs. You can use the Python IDE 3.3.0 to edit these files. The code for the called_process.py file is shown as here. The code for the calling_process.py file is shown here. To run the example, open the calling_process.py program with the Python IDE as shown here. You'll see the following output. We have two processes running to close the command prompt. Simply press the Enter button on the keyboard to do so. In this example, the execVP function starts a new process, replacing the current one. Note that the goodbye message is never printed. Instead, it searches for the program called process.py along the standard path, passes the contents of the second argument tuple as individual arguments to that program, and runs it with the current set of environment variables. The instruction input parentheses in called process.py is only used to manage the closure of OS prompt. In the video dedicated to process-based parallelism, we will finally see how to manage a parallel execution of more processes via the multiprocessing Python module. Nice! So now we know how to work with processes in Python. Next, we'll see how to work with threads in Python. In the previous video, we saw how to work with processes in Python. This video will explain how to work with threads in Python. A thread is an active flow of control that can be activated in parallel with other threads within the same process. The term flow control means a sequential execution of machine instructions. Each thread can execute a set of instructions, typically a function, independently and in parallel with other processes or threads. However, being the different active threads within the same process, they share space addressing and then the data structures. A thread is sometimes called a lightweight process because it shares many characteristics of a process, in particular the characteristics of being a sequential flow of control that is executed in parallel with other control flows that are sequential. The term light is intended to indicate that the implementation of a thread is less onerous than one of a real process. However, unlike the processes, multiple threads may share many resources, in particular space addressing and then the data structures. Let's take a look at a few differences between processes and threads. 1. A process can consist of multiple parallel threads. 2. Normally, the creation and management of a thread by the operating system is less expensive in terms of the CPU's resources than the creation and management of a process. Threads are used for small tasks, whereas processes are used for more heavyweight tasks, basically the execution of applications. 3. The threads of the same process share the address space and other resources, while processes are independent of each other. As mentioned earlier, thread-based parallelism is the standard way of writing parallel programs. However, the Python interpreter is not fully thread-safe. In order to support multi-threaded Python programs, a global lock called the Global Interpreter Lock, or GIL, is used. This means that only one thread can execute the Python code at the same time. Python automatically switches to the next thread after a short period of time, or when a thread does something that may take a while. The GIL is not enough to avoid problems in your own programs, although if multiple threads attempt to access the same data object, it may end up in an inconsistent state. In this video, we simply show you how to create a single thread inside a Python program. To execute this first example, we need the program hello python with threads.py shown here. To run the example, fire up your command prompt, navigate to your working directory, and run hello_python_ with threads.py file as shown. Note that hello_python_ with threads.py file is a standalone file. You'll see this output. While the main program has reached the end, the thread continues printing its message every 2 seconds. This example demonstrates what threads are, a subtask doing something in a parent process. A key point to make when using threads is that you must always make sure that you never leave any thread running in the background. This is very bad programming and can cause you all sorts of pain when you work on bigger applications. Awesome! So we saw how to work with threads in Python. Here we are at the end of this section. In this section, we saw how the parallel computing memory architecture works. We learned about the memory organization and parallel programming models. Later, we saw how to design a parallel programming model and evaluate its performance. We introduced Python and saw its importance in parallel world. In the end, we saw how to work with threads and processes in Python. In the next section, we'll learn about thread-based parallelism in detail. Welcome to the second section of this video course, Thread-Based Parallelism. In the previous section, we studied parallel computing in Python. In this section, we'll examine the features offered by the threading library with different application examples. We'll start off by defining a thread, and then we'll determine it. We'll also see how to use a thread in subclass and further understand how to do the thread synchronization. Later, we'll learn how to use a statement and carry out thread communication using queue. In the end, we'll evaluate the performance of multi-thread applications. Welcome to the first video of this section, titled Defining a Thread. In this video, we'll define a thread with the help of threading module. Further, we'll see how to instantiate a thread. Finally, we'll pass an argument to the function. First, let's understand how to use the Python threading module. Python manages a thread via the threading package that is provided by the Python standard library. This module provides some very interesting features that make the threading-based approach a whole lot easier. In fact, the threading module provides several synchronization mechanisms that are very simple to implement. The major components of the threading module are 1. The thread object. 2. The lock object. 3. The rlock object. 4. The semaphore object. 5. The condition object. And 6. The event object. Now let's define a thread. The simplest way to use a thread is to instantiate it with a target function and then call the start parentheses method to let it begin its work. The Python module threading has the thread parentheses method that is used to run processes and functions in a different thread. In the code which you can see on your screen, there are keywords such as 1. Group. This is the value of group that should be none. This is reserved for future implementations. 2. Target. This is the function that is to be executed when you start a thread activity. 3. Name. This is the name of the thread. By default, a unique name of the form thread_in is assigned to it. 4. Args. This is the tuple of arguments that are to be passed to target. 5. Kwargs. This is the dictionary of keyword arguments that are to be used for the target function. It's useful to spawn a thread and pass arguments to it that tell it what work to do. This example passes a number, which is the thread number, and then prints out the result. Let's see how to define a thread with the threading module. For this, a few lines of code are necessary. To import the threading module, we simply use the Python command as shown. In the main program, we instantiate a thread using the thread object with a target function called function. Also, we pass an argument to the function that will be included in the output message. The thread doesn't start running until the start method is called. and that join method makes the calling thread wait until the thread has finished the execution. Let's run this code and see the output. Open your command prompt and navigate to your working directory. Then run the Python file as shown. The output of the code looks like this. We should also point out that the output could be achieved in a different manner. In fact, multiple threads might print out the result back to stdout at the same time, so the output order cannot be predetermined. Great! So in this video we saw how to define a thread. Our next video shows us how to determine the current thread. In the previous video we defined a thread. In this video we'll determine a thread by creating the target functions and importing the time module. Let's get going. We'll now determine the thread defined earlier. Using arguments to identify or name the thread is cumbersome and unnecessary. Each thread instance has a name with a default value that can be changed as the thread is created. Naming threads is useful in server processes with multiple service threads that can handle different operations. To determine which thread is running, we create 3 target functions and import the time module to introduce a suspend execution of 2 seconds. For that we use the code shown. We instantiate a thread with the target function as shown here. Also, we pass the name that is to be printed, and if it's not defined, the default name will be used. Then we call the start parentheses and join parentheses methods on them as you can see here. Let us now run the code. For that, we'll open the command prompt and navigate to the working directory. We'll then run the Python file. The output of this should be as shown on screen. Nice! So we have successfully determined the thread. In the next video, we'll see how to use a thread in a subclass. In the previous video, we saw how to determine a thread. We now move on to the third video of this section, using a thread in a subclass. In this video, we'll define a new subclass. Then we'll override a method to add additional arguments. Further, we'll override a method to implement what the thread should do when it's started. After creating a new subclass, we'll create an instance of it and then start a new thread. So let's begin. We'll now see how to use a thread in a subclass. To implement a new thread using the threading module, you have to do the following. 1. Define a new subclass of the thread class. 2. Override this method to add additional arguments. 3. Then you need to override the runSelfArgs method to implement what the thread should do when it started. Once you've created the new thread subclass, you can create an instance of it and then start a new thread by invoking the start method, which will in turn call the run method. To implement a thread in a subclass, we define the myThread class. It has 2 methods that must be overridden with the thread's arguments. The threading module is the preferred form for creating and managing threads. Each thread is represented by a class that extends the thread class and overrides its run method. Then, this method becomes the starting point of the thread. In the main program, we create several objects of the myThread type. The execution of the thread begins when the start method is called. Calling the constructor of the thread class is mandatory. Using it, we can redefine some properties of the thread as the name or group of the thread. The thread is placed in the active state of the call-to-start method and remains there until it ends the run method, or you throw an unhandled exception to it. The program ends when all the threads are terminated. The join command must handle the termination of threads. Let's run the Python file to obtain the output. Open your command prompt and run the file using the command shown. The output produced will look like this. Awesome! So now we know how to use a thread in a subclass. In our next video, we'll focus on thread synchronization with lock. In the previous video, we saw how to use a thread in a subclass. Welcome to the 4th video of this section, thread synchronization with lock. In this video, we'll see how to manage a thread through the mechanism of lock parentheses. So let's begin with thread synchronization with lock. When 2 or more operations belonging to concurrent threads try to access the shared memory and at least one of them has the power to change the status of the data without a proper synchronization mechanism, a race condition can occur and it can produce invalid code execution and bugs and unexpected behavior. The easiest way to get around the race condition is the use of a lock. The operation of a lock is simple. When a thread wants to access a portion of shared memory, it must necessarily acquire a lock on that portion prior to using it. In addition to this, after completing its operation, the thread must release the lock that was previously obtained so that a portion of the shared memory is available for any other thread that wants to use it. In this way, it is evident that the impossibility of incurring races is critical, as the need of the lock for the thread requires that at a given instant, only a given thread can use this part of the shared memory. Despite their simplicity, the use of a lock works. However, in practice, we can see how this approach can often lead the execution to a bad situation of deadlock. A deadlock occurs due to the acquisition of a lock from different threads. It's impossible to proceed with the execution of operations since the various locks between them block access to the resources. For the sake of simplicity, let's think of a situation as shown in the figure wherein there are two concurrent threads, thread A and thread B, who have at their disposal resources 1 and 2. Suppose thread A requires resource 1 and thread B requires resource 2. In this case, both threads require their own lock, and up to this point everything proceeds smoothly. Imagine, however, that subsequently before releasing the lock, thread A requires a lock on resource 2 and thread B requires a lock on resource 1, which is now necessary for both the processes. Since both resources are locked, the two threads are blocked and waiting for each other until the occupied resource is released. The situation is the most emblematic example of the occurrence of a deadlock situation. As said, therefore, showing the use of locks to ensure synchronization so that you can access the shared memory on one hand is a working solution, but on the other hand, it is potentially destructive in certain cases. Lock allows us to restrict the access of a shared resource to a single thread or a single type of thread at that time. Before accessing the shared resource of the program, the thread must acquire the lock and must then allow any other threads access to the same resource. The code which we can see demonstrates how you can manage a thread through the mechanism of lock. In this code, we have two functions, increment and decrement, respectively. The first function increments the value of the shared resource, while the second function decrements the value, where each function is inserted in a suitable thread. In addition to this, each function has a loop in which the increase or decrease is repeated. We want to make sure, through the proper management of the shared resources, that the result of the execution is equal to the value of the shared variable that is initialized to 0. The sample code is shown here, where each feature within the sample code is properly commented. In the main method, we have the procedures which are shown here. For thread starting, use this. For thread joining, use this. In the increment with lock and decrement with lock functions, you can see how to use lock management. When you need to access the resource, call acquire method to hold the lock. This will wait for the lock to be released if necessary, and call release method to release it. Now let us run the code and see the output. Go to your command prompt and navigate to your working directory and run the Python file. As you can see, we have the correct result with the appropriate management and lock instructions. Note again that the result for the shared variable without the lock management could differ from the result shown. Let's recap. 1. Locks have two states, locked and unlocked. 2. We have two methods that are used to manipulate the locks, acquire parentheses and release parentheses. The following are the rules. 1. If the state is unlocked, a call to acquire parentheses changes the state to locked. If the state is locked, a call to acquire parentheses blocks until another thread calls release parentheses. 3. If the state is unlocked, a call to release parentheses raises a runtime error exception. 4. If the state is locked, a call to release parentheses changes the state to unlocked. Despite their theoretical smooth running, the locks are not only subject to harmful situations of deadlock, but also have many other negative aspects for the application as a whole. This is a conservative approach which, by its nature, often introduces unnecessary overhead. It also limits the scalability of the code and its readability. Furthermore, the use of a lock is decidedly in conflict with the possible need to impose the priority of access to the memory shared by the various processes. Finally, from a practical point of view, an application containing a lock presents considerable difficulties when searching for errors or debugging. In conclusion, it would be appropriate to use alternative methods to ensure synchronized access to shared memory and avoid race conditions. So in this video, we saw thread synchronization with lock. In the next video, we'll go through thread synchronization with rlock. In the previous video, we saw thread synchronization with lock. Here we are at the fifth video of this section, thread synchronization with rlock. In this video, we'll introduce a class with methods add and remove. Further, we'll carry out the rlock parentheses call within the class. If we want only the thread that acquires a lock to release it, we must use a rlock object. Similar to the lock object, the rlock object has two methods, acquire and release. Rlock is useful when you want to have a thread-safe access from outside the class and use the same methods from inside the class. In the sample code shown here, we have introduced the box class, which has the methods add and remove respectively, that provide us access to the execute method so that we can perform the action of adding or deleting an item, respectively. Access to the execute method is regulated by rlock function. In the main program, we repeated what was written in the example shown earlier. The two threads T1 and T2 are with the associated functions adder and remover. The functions are active when the number of items is greater than 0. The call to rlock parentheses is carried out inside the box class as shown here. The two functions, adder and remover, interact with the items of the box class respectively, and call the box class methods add and remove. In each method call, a resource is captured and then released. As for the lock object, rlock owns the acquire and release methods to acquire and release the resource. Now open the command prompt and go to the working directory. Run the Python command as shown. The execution result of the rlock parentheses object's example is as shown. As you can see, it is adding one item as well as removing one item. So we saw the process of thread synchronization with rlock. In the next video, we'll carry out the thread synchronization with semaphores. In the previous video, we studied the thread synchronization with rlock. We moved to the sixth video of this section, thread synchronization with semaphores. In this video, we'll use the consumer-produced model and initiate the semaphore to 0. We'll then carry out the synchronization process via semaphores. Invented by E. Dijkstra and used for the first time in the operating system, a semaphore is an abstract data type managed by the operating system used to synchronize the access by multiple threads to shared resources and data. Essentially, a semaphore is constituted of an internal variable that identifies the number of concurrent accesses to a resource to which it is associated. Also, in the threading module, the operation of a semaphore is based on the two functions acquire parentheses and release parentheses, as explained. 1. Whenever a thread wants to access a resource that is associated with a semaphore, it must invoke the acquire parentheses operation, which decreases the internal variable of the semaphore and allows access to the resource if the value of this variable appears to be non-negative. If the value is negative, the thread would be suspended and the release of the resource by another thread will be placed on hold. 2. Whenever a thread has finished using the data or shared resource, it must release the resource through the release parentheses operation. In this way, the internal variable of semaphore is incremented, and the first waiting thread in the semaphore's queue will have access to the shared resource. Although at first glance, the mechanism of semaphores does not present obvious problems, it works properly only if the wait and signal operations are performed in atomic blocks. If not, or if one of the two operations is stopped, this could arise unpleasant situations. Suppose that two threads execute simultaneously. The operation waits on a semaphore, whose internal variable has the value 1. Also assume that after the first thread has the semaphore decremented from 1 to 0, the control goes to the second thread, which decrements the light from 0 to -1 and waits as the negative value of the internal variable. At this point, with the control that returns to the first thread, the semaphore has a negative value and therefore the first thread also waits. Therefore, despite the semaphore having access to a thread, the fact that the wait operation was not performed in atomic terms has led to a solution of the stall. The next code describes the problem, where we have two threads, producer parentheses and consumer parentheses, that share a common resource, which is the item. The task of the producer parentheses is to generate the item while the consumer parentheses thread's task is to use the item produced. If the item has not yet produced the consumer parentheses thread, it has to wait. As soon as the item is produced, the producer parentheses thread notifies the consumer that the resource should be used. In this example, we use the consumer-producer model to show you the synchronization via semaphores. When the producer creates an item, it releases the semaphore. Also, the consumer acquires it and consumes the shared resource. The synchronization process done via the semaphores is shown in the following code. Initializing a semaphore to 0, we obtain a so-called semaphore event whose sole purpose is to synchronize the computation of two or more threads. Here, a thread must necessarily make use of data or common resources simultaneously. This operation is very similar to that described in the lock mechanism of the lock. The producer method thread creates the item and after that frees the resource by calling this function. The semaphore's release method increments the counter and then notifies the other thread. Similarly, the consumer method acquires the data by this method. If the semaphore's counter is equal to 0, it blocks the conditions acquire method until it gets notified by a different thread. If the semaphore's counter is greater than 0, it decrements the value. Finally, the acquired data is then printed on the standard output. Now let's run the Python file in the command prompt as shown. This is the result that we get after the file runs. A particular use of semaphores is the mutex. A mutex is nothing but a semaphore with an internal variable initialized to the value 1, which allows the realization of mutual exclusion in access to data and resources. Semaphores are still commonly used in programming languages that are multi-threaded. However, using them you can run into situations of deadlock. For example, there is a deadlock situation created when the thread T1 executes a wait on the semaphore S1, while the T2 thread executes a wait on the semaphore S1, and then T1, and then executes a wait on S2 and T2, and then it executes a wait on S1. In this video, we carried out thread synchronization with semaphores. In the next video, we'll see how to carry out thread synchronization with a condition. Our previous video showed us the process of thread synchronization with semaphores. This is the 7th video, thread synchronization with a condition. In this video, we illustrate the condition mechanism and carry out the thread synchronization with condition. A condition identifies a change of state in the application. This is a synchronization mechanism where a thread waits for a specific condition and another thread notifies that this condition has taken place. Once the condition takes place, the thread acquires the lock to get exclusive access to the shared resource. A good way to illustrate this mechanism is by looking again at a producer-consumer problem. The class producer writes to a buffer as long as it's not full, and the class consumer takes the data from the buffer, eliminating them from the latter, as long as the buffer is full. The class producer will notify the consumer that the buffer is not empty, while the consumer will report to the producer that the buffer is not full. To show you the condition mechanism, we'll again use the consumer-producer model as shown in this example. The class consumer acquires the shared resource that is modeled through the list items using condition.acquire. If the length of the list is equal to 0, the consumer is placed in a waiting state as shown. Otherwise, it makes a pop operation from the items list. So the consumer state is notified to the producer and the shared resource is released. The class producer acquires the shared resource and then it verifies that the list is completely full. In our example, we place the maximum number of items, 10, that can be contained in the items list. If the list is full, then the producer is placed in the wait state until the list is consumed. If the list is not full, a single item is added. The state is notified and the resource is released. Now let us run this code. Open the command prompt and run the Python file as shown here. This is the result that we get after a single run. The producer notifies the total items produced and consumer notifies total items consumed. This will continue till producer produces 10 items and consumer consumes 10 items. It's interesting to see the Python internals for the condition synchronizations mechanism. The internal class condition creates an rlock object if no existing lock is passed the class's constructor. Also, the lock will be managed when acquire and released are called. In this video, we saw the thread synchronization with a condition. In the next video, we check out the thread synchronization with an event. In the previous video, we saw the thread synchronization with a condition. We have reached the 8th video of the section, thread synchronization with an event. In this video, we'll understand the thread synchronization through the event object with the help of the producer-consumer problem. Events are objects that are used for communication between threads. A thread waits for a signal while another thread outputs it. Basically, an event object manages an internal flag that can be set to true with the set method and reset to false with the clear method. The wait method blocks until the flag is true. To understand the thread synchronization through the event object, let's take a look again at the producer-consumer problem. You can see the producer class is initialized with the list of items and the event function. Unlike the example with condition objects, the item list is not global, but it is passed as a parameter. In the run method for each item that is created, the producer class appends it to the list of items and then notifies the event. There are 2 steps that you need to take for this, and the first step is self.event.set function. The second step is self.event.clear function. The consumer class is initialized with the list of items in the event function. In the run method, the consumer waits for a new item to consume. When the item arrives, it is popped from the item list. Let's run the code now. Open your command prompt and navigate to your working directory. Run the command for Python file. This is the output that we get when we run the program. The T1 thread appends a value to the list and then sets the event to notify the consumer. The consumer's call to wait function stops blocking and the integer is retrieved from the list. All the operations between the producer and the consumer classes can be easily resumed with the help of the schema shown. Awesome! So we know now how to carry out the thread synchronization with an event. In the next video, we'll see how to use the with statement. In the previous video, we saw thread synchronization with event. This is the 9th video, using the with statement. In this video, we will see the use of objects such as lock, rlock, condition, and semaphore, which can be used as context managers for a with statement. We will basically test all these objects using the with statement. Python's with statement was introduced in Python 2.5. It's useful when you have two related operations that must be executed as a pair with a block of code in between. Also, with the with statement, you can allocate and release some resource exactly where you need it. For this reason, the with statement is called a context manager. In the threading module, all the objects provided by the acquire function and release function methods may be used in a with statement block. So the following objects can be used as context managers for a with statement. 1. Lock. 2. rlock. 3. Condition. And 4. Semaphore. In this code example, we simply test all the objects using the with statement. This code example shows the basic use of the with statement. We have a set with the most important synchronization primitives, so we test them by calling each one with the with statement. In the main program, we have defined a list, threading_synchronization_list, of thread communication directives that are to be tested. After defining them, we pass each object in the for cycle. Finally, we have two target functions, in which the threading with tests the with statement. In the example shown, we have used the Python support for logging. It embeds the thread name in every log message using the formatter code's modulo thread name s statement. The logging module is thread safe, so the messages from different threads are kept distinct in the output. Let's run the code now for the output. Open your command prompt and navigate to your working directory. Now run your Python file as shown. The output shows the use of the with statement for each function and also where it is not used. Wonderful! So now we know how to use a with statement. Next video will show us thread communication using a queue. In the previous video, we saw the use of with statement. Welcome to the 10th video titled Thread Communication Using a Queue. In this video, we'll take a look at the queue methods such as put, get, task done, and join. As discussed earlier, threading can be complicated when threads need to share data or resources. As we saw, the Python threading module provides many synchronization primitives, including semaphores, condition variables, events, and locks. While these options exist, it is considered a best practice to instead concentrate on using the module queue. Queues are much easier to deal with and make threaded programming considerably safer, as they effectively funnel all access to a resource of a single thread and allow a cleaner and more readable design pattern. We will simply consider these four queue methods. 1. Put function. This puts an item in the queue. 2. Get function. This removes and returns an item from the queue. 3. Task done function. This needs to be called each time an item has been processed. 4. Join function. This blocks until all items have been processed. In this example, we'll see how to use the threading module with the queue module. Also, we have two entities here that try to share a common resource, a queue. The code is as shown. First, the producer class. We don't need to pass the integers list because we use the queue to store the integers that are generated. The thread in the producer class generates integers and puts them in the queue in a for loop. The producer uses queue.putItemBlockTimeout to insert data into the queue. It has the logic to acquire the lock before inserting data in a queue. There are two possibilities. 1. If optional args block is true and timeout is none, this is the default case that we used in the example, it's necessary for us to block until a free slot is available. If timeout is a positive number, it blocks at most timeout seconds and raises the full exception if no free slot is available within that time. 2. If the block is false, put an item in the queue if a free slot is immediately available. Otherwise, raise the full exception. Timeout is ignored in this case. Here, put function checks whether the queue is full and then calls wait function internally, and after this, the producer starts waiting. Next is the consumer class. The thread gets the integer from the queue and indicates that it is done working on it using task done function. The consumer uses queue.getBlockTimeout and acquires the lock before removing data from the queue. If the queue is empty, it puts the consumer in a waiting state. Finally, in the main, we create the T1 thread for the producer and T2 and T3 for the consumer class. Let's run this code and see the output. For that, open the command prompt and navigate to the working directory. Run the Python file. After running the code, you should have an output similar to this. All the operations between the producer class and the consumer class can easily be resumed with the schema shown. Great! This video showed us how to carry out thread communication with the help of queue. In the next video, we'll evaluate the performance of multi-thread applications. In the previous video, we saw the thread synchronization with Q. Here we are at the last video of this section, evaluating the performance of multi-thread applications. In this video, we'll perform a total of 3 tests, and for each thread, we will use a different function. The GIL, as described in the previous section, is the lock introduced by the C Python interpreter. The GIL prevents parallel execution of multiple threads in the interpreter. Before being executed, each thread must wait for the GIL to release the thread that is running. In fact, the interpreter forces the executing thread to acquire the GIL before it accesses anything on the interpreter itself as the stack and instances of Python objects. This is precisely the purpose of GIL. It prevents concurrent access to Python objects from different threads. The GIL then protects the memory of the interpreter and makes the garbage work in the right manner. The fact is that the GIL prevents the programmer from improving the performance by executing threads in parallel. If we remove the GIL from the C Python interpreter, the threads would be executed in parallel. The GIL does not prevent a process from running on a different processor, it simply allows only one thread at a time to turn inside the interpreter. The next code is a simple tool that is used to evaluate the performance of a multi-threaded application. Each test calls a function only once in 100 loop iterations. Then we'll see the fastest among the 100 calls. In the for loop, we call the non_threaded and threaded functions. Also, we iterate the tests that increase the number of calls and threads. We will try with 1, 2, 3, 4, and 8 at the end of calls threads. In the non-threaded execution, we simply call the function sequentially the same number of times corresponding to those threads that we would use. To keep things simple, all the measurements of the speed of execution are provided by the Python's module timer. This module is designed to evaluate the performance of pieces of Python code, which are generally single statements. The code used is as shown. We've performed a total of 3 tests, and for each head, we use a different function, changing the function code function_to_run function defined in the sample code. The machine used for these tests is a Core 2 Duo CPU, 2.33 GHz. Let's carry out the first test. In this test, we simply evaluate the MC function as shown in the code. It'll show us the overhead associated with each mechanism that we're testing. Let's test this code. Open your command prompt and navigate to a working directory. Run the Python file. If we look at the results, we see how the thread calls are more expensive than the calls without threads. In particular, we also note how the cost of adding the thread is proportional to their number. In our example, we have 4 threads with 0.000301 seconds, while with 8 threads, we employ 0.000603 seconds. We will now carry out the second test. A typical example of threaded applications is the processing of numbers. Let's take a simple method to calculate the brute force of the Fibonacci sequence. Note that there is no sharing of the state here, just try to include more tasks that generate sequences of numbers. We will then make some changes here. Let's run the output as shown. As we can see from the output, we get no advantage by increasing the number of threads. The function is executed in Python, and because of the overhead for creating threads and GIL, the multi-threaded example can never be faster than the non-threaded example. Again, let's remember that the GIL allows only one thread at a time to access the interpreter. Here's the third test. This test consists in reading 1,000 times a block of data, 1 kilobyte, from test.data file. The function tested is as shown. These are the results of the test. We've begun to see a better result in the multi-threading case. In particular, we've noted how the threaded execution is half time consuming if we compare it with the non_threaded one. Let's remember that in real life we would not use threads as a benchmark. Typically, we would put the threads in a queue, pull them out, and perform other tasks. Having multiple threads that execute the same function, although useful in certain cases, is not a common use case for a concurrent program unless it divides the data in the input. In this section, we have seen the use of the Python threading module followed by how we can define and determine a thread. We then saw the use of a thread in a subclass. Later, we carried out the thread synchronization with lock, rlock, semaphores, condition, and events. Further, we saw the use of with statement and carried out thread communication with queue. In the end, we saw how to evaluate the performance of multi-thread applications. In the next section, we'll see the process-based parallelism. Hi, welcome to the third section of this course, Process-Based Parallelism. In the previous section, we saw how to use threads to implement concurrent applications. This section will examine the process-based approach. In particular, the focus is on two libraries, the Python multiprocessing module and the Python MPI4py module. Let's begin with the first video of this section, spawning a process. In this video, we'll create a series, 5, of processes and then run it. The term spawn means the creation of a process by a parent process. The parent process can, of course, continue its execution asynchronously or wait until the child process ends its execution. The multiprocessing library of Python allows the spawning of a process through these steps. 1. Build the object process. 2. Call its start method. This method starts the process's activity. 3. Call its join method. It waits until the process has completed its work and exited. This code example shows you how to create a series, or 5, of processes. Each process is associated with the function or I, where I is the ID associated with the process that contains it. To run the process and display the results, let's open the command prompt, preferably in the folder containing the example file, named spawn_a_process.py, and then type the command as shown. We obtain the following output using this command. Let's see how this works. As explained in the introduction section of this video, to create the object process, we must first import the multiprocessing module with this command. Then we create the object process in the main program using this command. Further, we call the start method as shown. The object process has for argument the function to which the child process is associated. We also pass an argument to the function that takes into account the process in which the associated function is situated. Finally, we call the join method on the process created. Without p.join method, the child process will sit idle and not be terminated, and then you must manually kill it. This reminds us once again of the importance of instantiating the process object within the main section. This is because the child process created imports the script file where the target function is contained. Then, by instantiating the process object within this block, we prevent an infinite recursive call of such instantiations. A valid workaround is used to define the target function in a different script, and then imports it into the namespace. So, for our example, we could have this. Here, target_function.py is as shown. Let's run the code now. You can see the output is always similar to that shown here. Great! So in this video, we saw the process of spawning. In our next video, we'll check out how to name a process. In the previous video, we saw how to spawn a process. In this video, we'll see how to name a process. For that, we'll create a process with and without a name and then run it. In the previous example, we identified the processes and how to pass a variable to the target function. However, it's very useful to associate a name to the processes as debugging an application requires the processes to be well marked and identifiable. The procedure to name a process is similar to that described for the threading library. See the video, How to Determine the Current Thread in Section 2, Thread-Based Parallelism. In the main program, we create a process with a name and a process without a name. Here, the common target is the foo function. To run the process, open the command prompt and type the command as shown. This is the result that we get after using the command. Let's see how it works. The operation is similar to the procedure used for naming a thread. To name a process, we should provide an argument with the object's name as shown here. In this case, we call the foo_process. If the process child wants to know which its parent process is, it must use this statement. This statement will provide the name of the parent process. Awesome! So this video taught us how to name the process. In the next video, we'll learn how to run a process in the background. In the previous video, we saw how to name a process. Welcome to the third video, running a process in the background. In this video, we'll set the daemon parameter and execute the process in the background. Running a process in the background is a typical mode of execution of laborious processes that do not require your presence or intervention. And this course may be concurrent to the execution of other programs. The Python multiprocessing module allows us, through the daemonic option, to run background processes. To run a background process, simply follow this code. To run the script from the command prompt, type this command. The final output of this command will be as shown. To execute the process in background, we set the daemon parameter as true. The processes in the no background mode have an output, so the daemonic process ends automatically after the main program ends to avoid the persistence of running processes. Note that a daemonic process is not allowed to create child processes. Otherwise, a daemonic process would leave its children orphaned if it gets terminated when its parent process exits. Additionally, there are not Unix daemons or services. They are normal processes that will be terminated and not joined if non-daemonic processes have exited. Wonderful! So we saw how to run a process in the background. In the next one, we'll see how to kill a process. In the previous video, we saw how to run a process in the background. Let's begin with the fourth video of this section, killing a process. In this video, we'll create a process with a target function. We'll then see how to terminate the process. It's possible to kill a process immediately using the terminate method shown here. Also, we use the isAlive method to keep track of whether the process is alive or not. In this example, a process is created with the target function foo. After the start, we kill it with the terminate function. Let's run this code now. Open the command prompt and navigate to working directory. Run the Python file. This is the output we get when we use the command. We create the process and then monitor its lifetime by the isAlive method. Then we finish it with a call to terminate using the p.terminate method. Finally, we verify the status code when the process is finished and read the attribute of the exit code process. The possible values of exit code are as shown. 1. This means that no error was produced. 2. Greater than 0 means that the process had an error and exited that code. 3. Less than 0 means that the process was killed with a signal of -1 into exit code. For our example, the output value of the exit code is equal to -15. The negative value, -15, indicates that the child was terminated by an interrupt signal identified by the number 15. Brilliant! So in this video, we've successfully killed the process. In the next video, we'll show how to use a process in a subclass. In the previous video, we saw how to kill a process. Welcome to the fifth video, using a process in a subclass. In this video, we'll define a new subclass of the process class. We'll then override a method to add additional arguments and also to implement what process should when it started. To implement a custom subclass and process, we must 1. Define a new subclass of the process class. 2. Override the initself_args method to add additional arguments. 3. Override the runSelf_args method to implement what process should when it started. Once you've created the new process subclass, you can create an instance of it and then start by invoking the start method, which will in turn call the run method. We'll rewrite the first example in this manner. To run the script from the command prompt, type this command. The result of the command is as shown. Each process subclass could be represented by a class that extends the process class and overrides its run method. The method highlighted here is the starting point of process. In the main program, we create several objects of the type myProcess as shown. The execution of the thread begins when the start method is called. The join method command just handles the termination of processes. In this video, we saw how to use process in a subclass. In the next video, we'll see how to exchange objects between processes. In the previous video, we saw how to use a process in a subclass. In our sixth video, we'll see how to exchange objects between processes. For that, we will first use queue to exchange objects, and then use pipes to exchange objects. The development of parallel applications has the need for the exchange of data between processes. The multiprocessing library has two communication channels with which it can manage the exchange of objects, queues and pipes. Now let's see how to use queues to exchange objects. As explained earlier, it's possible for us to share data with a queue data structure. A queue returns a process shared queue. If thread and process safe and any serialized object, Python serializes an object using the pickable module, can be exchanged through it. In this example, we show you how to use a queue for a producer-consumer problem. The producer class creates the item and queues, and then the consumer class provides the facility to remove the inserted item. The multiprocessing class has its queue object instantiated in the main program. Then we create the two processes, producer and consumer, with the queue object as an attribute. The process producer is responsible for entering 10 items in the queue using its put method. The process consumer has the task of removing the items from the queue using the get method and verifying that the queue is not empty. If this happens, the flow inside the while loop ends with a break statement as shown here. Let's run this code now. Open your command prompt and navigate to your working directory. Then run the Python file. This is the output that we get after the execution. A queue has the joinAllQueue subclass. It has the following two additional methods. 1. Task done method. This indicates that a task is complete. For example, after the get method is used to fetch items from the queue, so it must only be used by queue consumers. 2. Join method. This blocks the processes until all the items in the queue have been achieved and processed. Using pipes to exchange objects. The second communication channel is the pipe data structure. A pipe does the following. 1. Returns a pair of connection objects connected by a pipe. 2. In this, every object has send-receive methods to communicate between processes. Here's a simple example with pipes. We have one process pipe that gives out numbers from 0 to 9, and another process that takes the numbers and squares them. Let's remember that the pipe function returns a pair of connection objects connected to a pipe. In the example, outPipe contains the numbers from 0 to 9, generated by the target function createItems function. In the second process, we have two pipes, the input pipe and the final output pipe that contains the results. These are finally printed as this. Let us run the code now and see the output. Open the command prompt and run the Python file by using this command. The output obtained is as shown. Great! So in this video, we saw how to exchange objects between processes. In our upcoming video, we'll see how to synchronize processes. In the previous video, we saw how to exchange objects between processes using queues and pipes. Here's our 7th video of the section, Synchronizing Processes. In this video, we'll check out the process management with the barrier. Multiple processes can work together to perform a given task. Usually they share data. It's important that the access to shared data by various processes does not produce inconsistent data. Processes that cooperate by sharing data must therefore act in an orderly manner in order to access that data. Synchronization primitives are quite similar to those encountered for the library in threading. They are as follows. 1. Lock. This object can be in one of the states, locked and unlocked. A lock object has two methods, acquire and release, to manage the access to a shared resource. 2. Event. This realizes simple communication between processes. One process signals an event and the other processes wait for it. An event object has two methods, set and clear, to manage its own internal flag. 3. Condition. This object is used to synchronize parts of a workflow in sequential or parallel processes. It has two basic methods. Wait function is used to wait for a condition, and notify all function is used to communicate the condition that was applied. 4. Semaphore. This is used to share a common resource, for example, to support a fixed number of simultaneous connections. 5. rlock. This defines the recursive lock object. The methods and functionality for rlock are the same as the threading module. 6. Barrier. This divides a program into phases as it requires all of the processes to reach it before any of them proceed. Code that is executed after a barrier cannot be concurrent with the code executed before the barrier. The example here shows the use of a barrier method to synchronize two processes. We have 4 processes, wherein process 1 and process 2 are managed by a barrier statement, while process 3 and process 4 have no synchronizations directives. In the main program, we created 4 processes as shown here. However, we also need a barrier and lock primitive. The parameter 2 in the barrier statement stands for the total number of processes that are to be managed. The test-with-barrier function executes the barrier's wait method. When the two processes have called the wait method, they are released simultaneously. Let's run this code now. Open the command prompt and navigate to your working directory. Then run the Python file. By running the script, we can see that process 1 and process 2 print out the same timestamps. This figure shows you how a barrier works with the two processes. In this video, we saw how to synchronize a process. In the next video, we'll see how to manage a state between processes. In the previous video, we saw how to synchronize the process. Welcome to the 8th video, Managing a State Between Processes. In this video, we'll first declare a manager and then create a data structure of type dictionary. Further, we'll launch the multiprocess and run the code for the output. Python multiprocessing provides a manager to coordinate shared information between all its users. A manager object controls a server process that holds Python objects and allows other processes to manipulate them. A manager has these properties. 1. It controls the server process that manages the shared object. 2. It makes sure the shared object gets updated in all processes when anyone modifies it. This is an example of how to share a state between processes. First, the program creates a manager list, shares it between n number of task workers, and every worker updates an index. After all workers finish, the new list is printed out to stdout. Let's see how it works. We declare the manager with this statement. In the next statement shown here, a data structure of the type dictionary is created. Then, the multiprocess is launched. Here, the target function task worker adds an item to the data structure dictionary. Finally, we get the output and all the dictionaries are printed out. Let's run this code and see the output. Open the command prompt and run the code as shown here. This is the output. Awesome! So we saw how to manage a state between processes. In the next video, we'll see how to use a process pool. In the previous video, we saw how to manage a state between processes. We now move on to the 9th video, using a process pool. In this video, we'll show how to implement a process pool to perform a parallel application. We'll then create a pool of 4 processes. Finally, we use the pool's map method to perform a simple calculation. The multiprocessing library provides the pool class for simple parallel processing tasks. The pool class has the following methods. 1. Apply method. It blocks until the result is ready. 2. Apply a sync method. This is a variant of the apply method which returns a results object. It is in an asynchronous operation that will not lock the main thread until all the child classes are executed. 3. Map method. This is the parallel equivalent of the map function built-in function. It blocks until the result is ready. This method chops the iterable data into a number of chunks that submits to the process pool as separate tasks. 4. Map async method. This is a variant of the map function method, which returns a results object. If a callback is specified, then it should be a callable, which accepts a single argument. When the result becomes ready, a callback is applied to it, unless the call failed. A callback should be completed immediately, otherwise the thread that handles the results will get blocked. This code example shows you how to implement a process pool to perform a parallel application. We create a pool of 4 processes shown here, and then we use the pool's map method to perform a simple calculation. The multiprocessing.pool method applies function squared to the input element to perform a simple calculation. The total number of parallel processes is 4. The pool.map method submits to the process pool as separate tasks. The parameter inputs is a list of integer from 0 to 100. The result of the calculation is stored in the pool outputs. Then the final result is printed using this. It's important to note that the result of the pool.map method is equivalent to Python's built-in function map, except that the processes run parallelly. Now let's run the code. Open the command prompt and navigate to your working directory. Next, run the Python file as shown. This is the result that we get after completing the calculation. Great! So in this video, we saw how to use a process pool. In the next video, we'll see how to use the MPI4PY Python module. In the previous video, we saw how to use a process pool. In this video, we'll see how to use the MPI4PY Python module. The Python programming language provides a number of MPI modules to write parallel programs. The most interesting of these is the MPI4PY library. It's constructed on the top of MPI 1 and 2 specifications and provides an object-oriented interface, which closely follows MPI 2 C++ bindings. A C MPI user could use this module without learning a new interface. Therefore, it's widely used as an almost full package of an MPI library in Python. The main applications of the module, which we'll be describing in this section, are 1. Point-to-point communication. 2. Collective communication. 3. Topologies. The installation procedure of MPI4PY using a Windows machine is as shown. For other operating systems, refer to this link. Download the MPI software library MPI-CH from the link shown. Next, open an admin command prompt by right-clicking on the command prompt icon and select Run as Administrator. Run msiexec impitch installation file.msi from the admin command prompt to install MPI-CH2. During the installation, select the option that installs impitch2 for all users. Run wmpI config and store the username password. Use your real Windows login name and password. Add this path to the system path. No need to reboot the machine. Check SMPD using SMPD status. It should return SMPD running on hostname. To test the execution environment, go to the examples directory and run cpi.exe using MPI-exec in for CPI. Download the Python installer pip. It'll create a pip.exe file in the scripts directory of your Python distribution. Then, from the command prompt, type this to install MPI4PY. Let's start our journey to the MPI library by examining the classic code or a program that prints the phrase "Hello World" on each process that is instantiated. To execute this code, type this command line. In MPI, the processes involved in the execution of a parallel program are identified by a sequence of non-negative integers called ranks. If we have a number p of processes that runs a program, the processes will then have a rank that goes from 0 to p-1. The function MPI that comes to us to solve this problem has the following function calls. This function returns the rank of the process that called it. The com argument is called a communicator, as it defines its own set of all processes that can communicate together, as shown here. Let's run the command shown on the screen. This is the result that we would get after we execute this code. It should be noted that for illustration purposes only, the stdout output will not always be ordered, as multiple processes can apply at the same time by writing on the screen and their operating system arbitrarily chooses the order. So we're ready for a fundamental observation. Every process involved in the execution of MPI runs the same compiled binary, so each process receives the same instructions to be executed. Wonderful! So now we know how to use the MPI4PY Python module. In the next video, we'll see point-to-point communication. In the previous video, we saw how to use the MPI4PY Python module. In this video, we'll check out the point-to-point communication. Here, we'll utilize the directives to exchange messages between different processes. One of the most important features among those provided by MPI is the point-to-point communication, which is a mechanism that enables data transmission between two processes, a process receiver and a process sender. The Python module MPI4PY enables point-to-point communication via two functions. 1. This sends data to the destination process identified by its rank in the communicator group. 2. This receives data from the source process, which is also identified by its rank in the communicator group. The com parameter, which stands for communicator, defines a group of processes that may communicate through message passing. In this example, we show you how to utilize com.send and com.receive directives to exchange messages between different processes. To run the script, open the command prompt and type this command. This is the output that you'll get after you run the script. We ran the example with a total number of processes equal to 9, so in the communicator group, com, we have 9 tasks that can communicate with each other. Also, to identify a task or processes inside the group, we use their rank value. We have 2 sender processes and 2 receiver processes. The process of rank equal to 0 sends numerical data to the receiver process of a rank equal to 4. Similarly, we must specify the receiver process of rank equal to 4. Also, we note that the com.receive statement must contain as an argument the rank of the sender process. For the other sender and receiver processes, the process of a rank equal to 1 and the process of a rank equal to 8 respectively, the situation is the same, but the only difference is the type of data. In this case, for the sender process, we have a string that is to be sent. For the receiver process of a rank equal to 8, the rank of the sender process is pointed out. This figure summarizes the point-to-point communication protocol in MPI4PY. It's a two-step process consisting of sending some data from one task, sender, and of receiving these data by another task, receiver. The sending task must specify the data to be sent and their destination, the receiver process, while the receiving task has to specify the source of the message to be received. The com.send and com.receive functions are blocking functions. They block the caller until the buffered data involved can be safely used. Also, in MPI, there are 2 management methods of sending and receiving messages. 1, the buffered mode, and 2, the synchronous mode. In the buffered mode, the flow control returns to the program as soon as the data to be sent has been copied to a buffer. This does not mean that the message is sent or received. In the synchronous mode, however, the function only gets terminated when the corresponding receive function begins receiving the message. Amazing! So we carried out the point-to-point communication in this video. In the next video, we'll see how to avoid deadlock problems. In the previous video, we carried out point-to-point communication. This is the 12th video, Avoiding Deadlock Problems. In this video, we'll first introduce a typical deadlock problem, and then run a solution that allows us to avoid deadlocks by swapping the sending and receiving functions so as to make them asymmetrical. A common problem we face is that of the deadlock. This is a situation where two or more processes block each other and wait for the other to perform a certain action that serves to another, and vice versa. The MPI4PY module doesn't provide any specific functionality to resolve this, but only some measures, which the developer must follow to avoid problems of deadlock. Let's first analyze the following Python code, which will introduce a typical deadlock problem. We have two processes, rank equal to 1 and rank equal to 5, that communicate with each other and both have the data sender and data receiver functionality. If we try to run this program, we note that none of the two processes are able to respond. Both prepare to receive a message from the other and get stuck there. This happens because the function MPI com.receive as well as the com.send MPI blocks them. It means that the calling process waits for their completion. As for the com.send MPI, the completion occurs when the data has been sent and may be overwritten without modifying the message. The completion of the com.receive MPI instead is when the data has been received and can be used. To solve the problem, the first idea that occurs is to invert the com.receive MPI with the com.send MPI in this way. This solution, however, even if correct from the logical point of view, not always ensures the avoidance of a deadlock. Since the communication is carried out through a buffer where the com.send MPI copies the data to be sent, the program runs smoothly only if this buffer is able to hold them all. Otherwise, there is a deadlock. The sender cannot finish sending data because the buffer is committed, and the receiver cannot receive data as it's blocked by a com.send MPI, which is not yet complete. At this point, the solution that allows us to avoid deadlocks is used to swap the sending and receiving functions so as to make them asymmetrical in this manner. Now let's run this code to see the output. Enter this command. Let us type the print statement to see how it works. Finally, we get the correct output. The solution to the deadlock is not only solution. There is, for example, a particular function that unifies the single call that sends a message to a given process and receives another message that comes from another process. This function is called send-receive. As you can see, the required parameters are the same as the com.send MPI and the com.receive function MPI. Also, in this case, the function blocks, but compared to the two already seen previously, it offers the advantage of leaving the communication subsystem responsible for checking the dependencies between sending and receiving, thus avoiding the deadlock. In this way, the code of the previous example becomes as shown. Awesome! So we saw how to avoid the deadlock problem. In the next video, we'll see how to use broadcast for collective communication. In the previous video, we saw how to avoid deadlock problems. In this video, we'll see how to use a broadcast function for collective communication. During the development of a parallel code, we often find ourselves in the situation where we have to share between multiple processes the value of a certain variable at runtime or certain operations on variables that each process provides, presumably with different values. To resolve this type of situation, the communication trees are used. For example, the process 0 sends data to the processes 1 and 2, which respectively will take care of sending them to the processes 3, 4, 5, and 6, and so on. Instead, MPI libraries provide functions ideal for the exchange of information or the use of multiple processes that are clearly optimized for the machine in which they are performed. A communication method that involves all the processes belongs to a communicator is called a collective communication. Consequently, a collective communication generally involves more than two processes. However, instead of this, we'll call the collective communication broadcast, wherein a single process sends the same data to any other process. The MPI4PY functionalities in the broadcast are offered by this method. The function simply sends the information contained in the message process route to every other process that belongs to the COM communicator. Each process must, however, call it by the same values of root and COM. Here's an example wherein we've used the broadcast function. We have a root process of rank equal to 0 that shares its own data, variable to share, with the other processes defined in the communicator group. The output obtained with a communicator group of 10 processes is: the process root of rank 0 instantiates a variable, variable to share, equal to 100. This variable will be shared with the other processes of the communication group. To perform this, we also introduce the broadcasting communication statement, which is this. Here, the parameters in the function are the data to be shared and the root process or main sender process. Finally, the print statement visualizes the rank of the running process and the value of its variable. Now let's run the code. Open the command prompt and run the Python file as shown. The output obtained with the communicator group of 10 processes. When we run the code, in our case, we have a communication group of 10 processes, where variable to share is shared between the other processes in the group. Collective communication allows simultaneous data transmission between multiple processes in a group. In MPI-4PY, the collective communication are provided only in their blocking version. They block the caller method until the buffer data involved can safely be used. The most commonly collective operations are 1. Barrier synchronization across the group's processes. 2. Communication functions. Here we have A. Broadcasting data from one process to all processes in the group. B. Gathering data from all processes to one process. And C. Scattering data from one process to all process. And 3. Reduction operation. Great! So now we saw how to carry out collective communication using broadcast. In our next video, we'll see how to carry out collective communication using scatter. In the previous method, we saw how to carry out collective communication using broadcast. In this video, we'll see how to distribute data to different processes using scatter. The scatter functionality is very similar to a scatter broadcast, but has one major difference. While com.bcast sends the same data to all listening processes, com.scatter can send the chunks of data in an array to different processes. This figure illustrates the functionality of scatter. The com.scatter function takes the elements of the array and distributes them to the processes according to their rank, for which the first element will be sent to the process 0, the second element to the process 1, and so on. The function implemented in MPI-4PY is as shown here. In the next example, we see how to distribute data to different processes using the scatter functionality. The process of rank 0 distributes the array to share data structure to other processes, as we can see here. The receiveBuf parameter indicates the value of the ith variable that will be sent to the ith process through the com.scatter statement. We also remark that one of the restrictions to com.scatter is that you can scatter as many elements as the processors you specify in the execution statement. In fact, attempting to scatter more elements than the processor specified, 3 in this example, will get you an error like this. Let's run the code and see the output. Open up your command prompt and run this Python file as shown. The output of the code is as shown. The MPI-4PY library provides 2 other functions that are used to scatter data. 1. This function sends data from one process to all of the processes in a communicator. 2. This function scatters data from one process to all of the processes in a group that provides different amount of data and displacements at the sending side. The sendBuf and receiveBuf arguments must be given in terms of a list, as in the point-to-point function com.send. Here, data must be a buffer-like object of the size dataSize and of the type dataType. Impressive, isn't it? We now know how to carry the collective communication using scatter. In our next video, we'll see how to carry out the collective communication using gather. In the previous video, we saw how to carry out collective communication using scatter. In this video, using gather for collective communication, we'll build the process data and send it to root processes. We'll then collect the data in an array. The gather function performs the inverse of the scatter functionality. In this case, all processes send data to a root process that collects the data received. The gather function implemented in MPI-4PY is, as shown here. Here, sendBuf is the data that is sent and rank of root process represents the process receiver of all the data. In this example, we wanted to represent just the conditions shown in the figure. Each process builds its own data that is to be sent to the root processes that are identified with a rank 0. Finally, we run the code with a group of processes equal to file. We have n processes sending their data. If the rank of the process is 0, then the data is collected in an array as shown. The gathering of data is given instead by this function. Let's run this code. Open the command prompt and enter the command to run the Python file. Finally, we run the code with a group of processes equal to file. The root process 0 receives data from the other 4 processes as we represented in the figure. To collect data, MPI-4PY provides the following functions. 1. Gathering to one task. com.gather, com.gatherv, and com.gather. 2. Gathering to all tasks. com.allgather, com.allgatherv, and com.allgather. Incredible! So we saw how to use gather for collective communication. Our next video shows us collective communication using all-to-all. In the previous video, we saw how to utilize gather function for collection communication. In this video, we'll go further to use all-to-all function for collective communication. We'll implement the all-to-all function and run the code with a communicated group of file processes. The all-to-all collective communication combines the scatter and gather functionality. In MPI-4PY, there are three types of all-to-all collective communication. 1. With this, the all-to-all scatter/gather sends data from all-to-all processes in the group. 2. With this, the all-to-all scatter/gather vector sends data from all-to-all processes in a group, providing different amount of data and displacements. 3. This generalized all-to-all communication allows different counts, displacements, and data types for each partner. In this example, we'll see a MPI-4PY implementation of com.all-to-all. We consider a communicated group of processes where each process sends and receives an array of numerical data from the other processes defined in the group. The com.all-to-all method takes the ith object from sendBuf of the task j and copies it to the jth object of the receiveBuf argument of the task I. We can also figure out what happened using this schema. These are our observations regarding the schema. 1. The process P0 contains the data array 0, 1, 2, 3, 4, where it assigns 0 to itself, 1 to the process P1, 2 to the process P2, 3 to the process P3, and 4 to the process P4. 2. The process P1 contains the data array 0, 2, 4, 6, 8, where it assigns 0 to P0, 2 to itself, 4 to the process P2, 6 to the process P3, and 8 to the process P4. 3. The process P2 contains the data array 0, 3, 6, 9, 12, where it assigns 0 to P0, 3 to the process P1, 6 to itself, 9 to the process P3, and 12 to the process P4. 4. The process P3 contains the data array 0, 4, 8, 12, 16, where it assigns 0 to P0, 4 to the process P1, 8 to the process P2, 12 to itself, and 16 to the process P4. 5. The process P4 contains the data array 0, 5, 10, 15, 20, where it assigns 0 to P0, 5 to the process P1, 10 to the process P2, 15 to the process P3, and 20 to itself. Let's run the code now. Open the command prompt and type this command. We run the code with a communicated group of 5 processes, and the output we get is as shown on the screen. All-to-all personalized communication is also known as total exchange. This operation is used in a variety of parallel algorithms such as the fast Fourier transform, matrix transpose, sample sort, and some parallel database join operations. In this video, we saw how to carry out collective communication using all-to-all. The next video will explain the reduction operation. In the previous video, we saw how to carry out collective communication using all-to-all. In this video, we'll implement a sum of an array of elements using reduction operation. Similar to com.gather, com.reduce takes an array of input elements in each process and returns an array of output elements to the root process. The output elements contain the reduced result. In MPI-4PY, we define the reduction operation through this statement. Com.reduce, sendBuf, receiveBuf, rank of the root process, op equals to type of reduction operation. We must note that the difference with the com.gather statement resides in the op parameter, which is the operation that you wish to apply to your data, and the MPI-4PY module contains a set of reduction operations that can be used. Some of the reduction operations defined by MPI are 1. MPI.max. This returns the maximum element. 2. MPI.min. This returns the minimum element. 3. MPI.sum. This sums up the elements. 4. MPI.prod. This multiplies all elements. 5. MPI.land. This performs a logical operation across the elements. 6. MPI.maxlog. This returns the maximum value in the rank of the process that owns it. 7. MPI.minlog. This returns the minimum value in the rank of the process that owns it. Now we'll see how to implement a sum of an array of elements with the reduction operation MPI.sum using the reduction functionality. Each process will manipulate an array of size 3. For array manipulation, we use the functions provided by the NumPy Python module. To perform the reduction sum, we use the com.reduce statement and also identify with rank 0 the root process, which will contain receiveBuf that represents the final results of the computation. Also, we must note that with the op equals MPI.sum option, we apply the sum operation to all of the elements of the column array. To better understand how the reduction operates, let's take a look at this figure. The sending operation is as follows. 1. The process P0 sends the data array 0, 1, 2. 2. The process P1 sends the data array 0, 2, 4. 3. The process P2 sends the data array 0, 3, 6. The reduction operation sums the ith elements of each task and then puts the result in the ith element of the array in the root process P0. For the receiving operation, the process P0 receives the data array 0, 6, 12. Let's run the code now. It makes sense to run the code with a communicator group of 3 processes, that is, the size of the manipulated array. In the command prompt, type this command and run the Python file. Finally, we obtain the result as shown. Brilliant! So now we saw how the reduction operation works. In our next video, we'll see how to optimize communication. In the previous video, we saw the process of reduction operation. In our last video, optimizing communication, we'll see how to implement a Cartesian topology. We'll then define a set of coordinates. An interesting feature that's provided by MPI concerns the virtual topologies. As already noted, all the communication functions, point-to-point or collective, refer to a group of processes. We've always used the MPI COM world group that includes all processes. It assigns a rank 0 to n-1 for each process that belongs to a communicator of the size n. However, MPI allows us to assign a virtual topology to a communicator. It defines a particular assignment of labels to the different processes. A mechanism of this type permits you to increase the execution performance. In fact, if you build a virtual topology, then every node will communicate only with its virtual neighbor, optimizing the performance. For example, if the rank was randomly assigned, a message could be forced to pass to many other nodes before it reaches the destination. Beyond the question of performance, a virtual topology makes sure that the code is more clear and readable. MPI provides 2 building topologies. The first construct creates Cartesian topologies, while the latter creates any kind of topologies. Specifically, in the second case, we must apply the adjacency matrix of the graph that you want to build. We'll deal only with Cartesian topologies, through which it is possible to build several structures that are widely used, which are mesh, ring, toroid, and so on. The function used to create a Cartesian topology is, as shown here. Here, number of rows and number of columns specify the rows and columns of the grid that's to be made. In this example, we see how to implement a Cartesian topology of the size m by n. Also, we define a set of coordinates to better understand how all the processes are disposed. The resulting topology is a mesh of 2 by 2. Refer to the previous figure for a mesh representation, the size of which is equal to the number of processes in the input, that is 4, as shown here. Then the Cartesian topology is built here. To find out the position of the ith process, we use the getCoords method in this form. The obtained topology is shown in the figure. To obtain a toroidal topology of the size m by n, we need these lines of code. This corresponds to the output as shown. Open the command prompt and run this command. For each process, the output should read as: if neighbor processes equals -1, then it has no topological proximity. Otherwise, neighbor processes shows the rank of the process closely. Also, it covers the topology represented here. Interesting. So we saw how to optimize the communication. In this section, we saw how to spawn, name, and kill the process. We also saw how to run a process in the background and use it in a subclass. Then we moved on to exchanging objects between processes and using a process pool. Further, we saw how to synchronize process and manage a state between the processes. We also witnessed how to use a process pool in the MPI 4py Python module. Later, we carried out the point-to-point communication and learned how to avoid deadlock problems. Next, we saw the process of collective communication using broadcast, scatter, gather, and all-to-all function. Also, we saw the reduction operation and the optimization of communication. In our next section, we learn asynchronous programming. In the previous section, we saw the process-based parallelism. Welcome to the 4th section, asynchronous programming. With the sequential and parallel execution model, there's a third model called the asynchronous model that is of fundamental importance to us along with the concept of event programming. In this section, we'll take a look at asynchronous programming through the medium of videos which we'll cover. 1. How to use the concurrent features Python module. 2. Event loop management with Essentio. 3. Handling coroutines with Essentio. 4. Task manipulation with Essentio. 5. Dealing with Essentio and features. Let's begin with our first video of this section titled Using the Concurrent Features Python Modules. In this video, we will manage concurrent programming tasks such as process and thread pooling with the help of Concurrent Feature Module. With the release of Python 3.2, the Concurrent Feature Module was introduced, which allows us to manage concurrent programming tasks such as process and thread pooling, non-deterministic execution flows, and processes and thread synchronization. This package is built by the following classes. 1. Concurrent Features Executor. This is an abstract class that provides methods to execute calls asynchronously. 2. Submit Function Argument. This schedules the execution of a function, called callable, on the arguments. 3. Map Function Argument. This executes the function on arguments in an asynchronous mode. 4. Shutdown, wait equals true. This signals the executor to free any resource. 5. Concurrent.futures.future. This encapsulates the asynchronous execution of a callable function. Future objects are instantiated by submitting tasks, functions with optional parameters, to executors. Executors are abstractions that are accessed through their subclasses, thread or process executor pools. In fact, instantiation of threads and process is a resource-demanding task, so it's better to pool these resources and use them as repeatable launchers or executors, hence the executors concept, for parallel or concurrent tasks. Let's look at how to deal with the process and thread pool. A thread or process pool, also called pooling, indicates a software manager that is used to optimize and simplify the use of threads and or processes within a program. Through the pooling, you can submit the task or tasks that are to be executed to the pooler. The pool is equipped with an internal queue of tasks that are pending and a number of threads or processes that execute them. A recurring concept in pooling is reuse. A thread or process is used several times for different tasks during its lifecycle. It decreases the overhead of creating and increasing the performance of the program that takes advantage of the pooling. Reuse is not a rule, but it is one of the main reasons that lead a programmer to use pooling in his or her application. The current.futures model provides two subclasses of the executor class, respectively, which manipulates a pool of threads and a pool of processes asynchronously. The two subclasses are as shown on the screen. 1. Concurrent.futures, thread pool executor max workers. 2. Concurrent.futures, process pool executor max workers. The max workers parameter identifies the max number of workers that execute the call asynchronously. This example shows you the functionality of process and thread pooling. The task to be performed is that we have a list of numbers from 1 to 10, number list. For each element of the list, a count is made up of 10 million, just to waste time, and then the latter number is multiplied with the ith element of the list. By doing this, the cases listed on the screen are evaluated. 1. Sequential execution. 2. A thread pool with 5 workers. Consider the code shown. We build a list of numbers stored in number list, and for each element in the list, we operate the counting procedure until 100 million iterations. Then we multiply the resulting value for 100 million. In the main program, we execute the task that will be performed in a sequential mode. Also, in parallel mode, we will use the concurrent.futures module's pooling capability for a thread pool. The thread pool executor executes the given task using one of its internally pooled threads. It manages file threads working on its pool. Each thread takes a job out of the pool and executes it. When the job is executed, it takes the next job to be processed from the thread pool. When all the jobs are processed, the execution time is printed. For the process pooling implemented by the process pool executor class, we have this code. Like thread pool executor, the process pool executor class is an executor subclass that uses a pool of processes to execute calls asynchronously. However, unlike thread pool executor, the process pool executor uses the multiprocessing module, which allows us to outflank the global interpreter lock and obtain a shorter execution time. The pooling is used in almost all server applications where there is a need to handle more simultaneous requests from any number of clients. Many applications, however, require that each task should be performed instantly, or you have more control over the thread that executes it. In this case, pooling is not the best choice. Let's run the code and see the output now. Open the command prompt and navigate to your working directory. Then run the Python file. After running the code, we have these results with the execution time. Great! So in this video, we saw the use of concurrent.futures Python modules. In our next video, we take a look at the event loop management with Essentio. In our previous video, we saw how to use the concurrent.futures Python modules. Welcome to the second video of this section, titled Event Loop Management with Essentio. In this video, we'll be defining asynchronous tasks, and then we'll run the code which will show the event loop management. The Python module Essentio provides facilities to manage events, coroutines, tasks, and threads, and synchronization primitives to write concurrent code. The main components and concepts of this module are 1. An event loop. The Essentio model allows a single event loop per process. 2. Coroutines. This is the generalization of the subroutine concept. Also, a coroutine can be suspended during the execution so that it waits for external processing, some routine in I/O, and returns from the point at which it had stopped when the external processing was done. 3. Futures. This defines the future object, such as the concurrent.futures module that represents a computation that has still not been accomplished. 4. Tasks. This is a subclass of Essentio that is used to encapsulate and manage coroutines in a parallel mode. In this video, the focus is on handling events. In fact, in the context of asynchronous programming, events are very important since they are inherently asynchronous. Within a computational system, the entity that can generate events is called an event source, while the entity that negotiates to manage an event is called the event handler. Sometimes there may be a third entity called an event loop. It realizes the functionality to manage all the events in a computational code. More precisely, the event loop acts cyclically during the whole execution of the program and keeps track of events that have occurred within a data structure to queue and then process them one at a time by invoking the event handler if the main thread is free. Finally, we report a pseudocode of an event loop manager. All the events in the while loop are caught and then processed by the event handler. The handler that processes an event is the only activity that takes place in the system. When the handler has ended, the control is passed on to the next event that is scheduled. Essentio provides methods that are used to manage an event loop, which are 1. Loop equals getEventLoop method. Using this, you can get the event loop for the current context. 2. Loop.callLater. Time delay callback argument. This arranges for the callback that is to be called after the given time delay seconds. 3. Loop.callSoon. Callback argument. This arranges for a callback that is to be called as soon as possible. The callback is called after callSoon returns and when the control returns to the event loop. 4. Loop.time. This returns the current time as a flat value according to the event loop's internal clock. 5. Essentio.setEventLoop. This sets the event loop for the current context to loop. 6. Essentio.newEventLoop. This creates and returns a new event loop object according to the policy's rules. 7. Loop.runForever. This runs until stop is called. In this example, we show you how to use the loop event statements provided by the Essentio library to build an application that works in an asynchronous mode. Let's consider this code. In this example, we defined 3 asynchronous tasks, where each task calls the subsequent in the order as shown in the figure. To accomplish this, we need to capture the event loop. Then we schedule the first call to function 1 by the callSoon construct as you can see here. Let's note the definition of function_1 using this code. This defines the asynchronous behavior of the application with the following arguments. 1. Endtime. This defines the upper time limit within function 1 and makes the call to function 2 through the callLater method. 2. Loop. This is the loop event that was captured previously with the getEventLoop method. The task of function 1 is pretty simple, which is to print its name, but it could also be more computationally intensive. After performing the task, it's compared to loop.time with the total length of the run. The total number of the cycles is 12, and if it's not past this time, then it is executed with a callLater method with a delay of 1 second. For function 2 and function 3, the operation is the same. If the running time expires, then the loop event must end. Let's run this file and see the output. Go to your command prompt and run this file. The output of the code will be something like this. Awesome! So we saw event loop management with Essentio. In our next video, we'll see how to handle coroutines with Essentio. In the previous video, we saw event loop management with Essentio. Here we are at the third video of this section, handling coroutines with Essentio. In this video, we'll define each state of the automata and determine to which state the finite state machine will be passed. We saw in the course of the various examples presented that when a program becomes very long and complex, it's convenient to divide it into subroutines, each of which realizes a specific task for which it implements a suitable algorithm. The subroutine cannot be executed independently, but only at the request of the main program, which is then responsible for coordinating the use of subroutines. Coroutines are a generalization of the subroutine. Like a subroutine, the coroutine computes a single computational step, but unlike subroutines, there is no main program that can be used to coordinate the results. This is because the coroutines link themselves together to form a pipeline without any supervising function responsible for calling them in a particular order. In a coroutine, the execution point can be suspended and resumed later after keeping track of its local state in the intervening time. Having a pool of coroutines, it's possible to interleave their computations, run the first one until it yields the control back, then run the second, and so on down the line. The control component of the interleave is the event loop, which was explained in the previous video. It keeps track of all the coroutines and schedules when they'll be executed. The other important aspects of coroutines are as follows. 1. Coroutines allow multiple entry points that can be yielded multiple times. 2. Coroutines can transfer the execution to any other coroutine. The term yield is used to describe a coroutine that pauses and passes the control flow to another coroutine. Since coroutines can pass values along with the control flow to another coroutine, the phrase yielding a value is used to describe the yielding and passing of a value to the coroutine that receives the control. To define a coroutine with the Essentio module, we simply use an annotation as shown here. In this example, we'll see how to use the coroutine mechanism of Essentio to simulate a finite state machine of 5 states. A finite state machine, or automaton, FSA, is a mathematical model that is widely used not only in engineering disciplines, but also in sciences, such as mathematics and computer science. The automata through which we want to simulate the behavior is as shown. In this diagram, we have indicated with S0, S1, S2, S3, and S4 the states of the system. Here, 0 and 1 are the values for which the automata can pass from one state to the next. This operation is called a transition. So, for example, the state S0 can be passed to the state S1 only for the value 1, and S0 can be passed to the state S2 only for the value 0. The Python code that follows simulates a transition of the automaton from the state S0, the so-called start state, up to the state S4, the end state. Each state of the automata has been defined with the annotation. For example, the state S0 is defined using this code. The transition to the next state is determined by input value, which is defined by the radiant01 function of Python's module random. The function provides randomly the values 0 or 1. In this manner, it randomly determines to which state the finite state machine will be passed. After determining the value at which the finite state machine will be passed, the coroutine calls the next coroutine using the command yield from. The variable result is the value that each coroutine returns. It is a string, and by the end of the computation, we can reconstruct the transition from the initial state of the automation, the start state, up to the final state, the end state. The main program starts the evaluation inside the event loop as shown here. Let's run the code and see the output. Open your command prompt and navigate to the working directory. Then run the Python file. After running the code, we have an output similar to this. Wonderful! So now we know how to handle coroutines with Essentio. In our next video, we'll see the process of task manipulation with Essentio. In the previous video, we saw how to handle coroutines with Essentio. This is the 4th video of this section, manipulating tasks with Essentio. In this video, we'll see how the 3 mathematical functions can be executed concurrently by the Essentio task function statement. Essentio is designed to handle asynchronous processes and concurrent task executions on an event loop. It also provides us with the Essentio.task class for the purpose of wrapping coroutines in a task. Its use is to allow independently running tasks to run concurrently with other tasks on the same event loop. When a coroutine is wrapped in a task, it connects the task to the event loop and then runs automatically when the loop is started, thus providing a mechanism to automatically drive the coroutine. The Essentio module provides us with the Essentio.task coroutine method to handle computations with tasks. It schedules the execution of a coroutine. A task is responsible for the execution of a coroutine object in an event loop. If the wrapped coroutine yields from a future, the task suspends the execution of the wrapped coroutine and waits for the completion of the future. When the future is complete, the execution of the wrapped coroutine restarts with the results or the exception of the future. Also, we must note that an event loop only runs one task at a time. Other tasks may run parallelly if other event loops run in different threads. While a task waits for the completion of a future, the event loop executes a new task. In this sample code, we've shown you how 3 mathematical functions can be executed concurrently by the Essentio.task statement. In this example, we defined 3 coroutines, factorial Fibonacci, and binomial coefficient, each of which, as explained previously, is identified by the Essentio.coroutine decorator. To perform these three tasks parallelly, we first put them in the list tasks in this manner. Then we get the event loop. Next, we run the tasks. Here, Essentio.wait statement, tasks, waits for the given coroutines to complete. In the last statement, we close the event loop. Now let's run the code and see the output. Open the command prompt and run the Python file as shown. The result of the code is as shown. Amazing! We just saw how to perform task manipulation with Essentio. In our next video, we'll deal with Essentio and futures. In the previous video, we carried our task manipulation with Essentio. This is the last video of the section dealing with Essentio and futures. In this video, we'll see how to use the futures class for the management of two coroutines, first coroutine and second coroutine. Another key component of the Essentio module is the future class. This is very similar to concurrent.futures, but of course, as it's adapted in the main mechanism of Essentio's event loop. The Essentio.future class represents a result, but can also be an exception, that is not yet available. It therefore represents an abstraction of something that is yet to be accomplished. Callbacks that have to process any results are in fact added to the instances of this class. To manage an object future in Essentio, we must declare these. The basic methods of this class are 1. Cancel method. This cancels the future and schedules callbacks. 2. Result method. This returns the result that this future represents. 3. Exception method. This returns the exception that was set on this future. 4. Add done callbacks function. This adds a callback that is to be run when future is executed. 5. Remove done callback function. This removes all instances of a callback from the call when done list. 6. Set result. This marks the future as complete and sets its result. 7. Set exception. This marks the future as complete and sets an exception. The following example shows you how to use the futures class for the management of two coroutines, first coroutine and second coroutine, that perform the tasks such as the sum of the first n integers and second, the factorial of n. The code is as shown on screen. In the main program, we define the object's future to associate the coroutines. While defining the tasks, we pass the object future as an argument of coroutines. Finally, we add a callback that is to be run when the future gets executed. Here, getResult is a function that prints the final results of the future. In the coroutine wherein we pass the object future as an argument, after the computation we set a sleep time of 3 seconds for the first coroutine and 4 seconds for the second coroutine. Then we mark the future as complete and set its result with the help of future.setResult function. Let's run this code and see the output. Open the command prompt and type the command shown to run the Python file. The output is obtained after multiple runs. If you change the arguments, your output will change. Swapping the sleep time between the coroutines, we invert the output results. We first do that for the second coroutine output. Let's see the output for this. We see that the outputs have swapped. Awesome! So we dealt with Essentio and futures in this video. With this, we've come to the end of this section. In this section, we saw how to use the concurrent.futures Python modules. We then studied the event loop management and handling coroutines with Essentio. Further, we carried out the task manipulation with Essentio. In the end, we saw how to deal with Essentio and futures. In our next section, we'll take a look at distributed Python. In our previous section, we got acquainted with asynchronous programming. Hi, welcome to the 5th section, Distributed Python. This section will introduce you to distributed computing. Here we'll be using Celery to distribute and create tasks. We'll then deal with scientific computing and handling map functions with Scoop. Further, we'll take a look at remote method invocation and chaining objects with Pyro4. We'll also develop a client-server application and communicating sequential processes with Pyro4. Finally, we'll see how to use MapReduce with Disco and how to carry out a remote procedure called RPYC. This is the first video of this section, using Celery to distribute tasks. In this video, we'll see how to install Celery, Message Broker, RabbitMQ, and Flower. We'll then use Celery to distribute tasks. Celery is a Python framework used to manage a distributed task following the object-oriented middleware approach. Its main feature consists of handling many small tasks and distributing them on a large number of computational nodes. Finally, the result of each task will then be reworked in order to compose the overall solution. To work with Celery, we need the following components. 1. The Celery module, of course. 2. A message broker. This is a Celery-independent software component, the middleware used to send and receive messages to distributed task workers. A message broker is also known as a message middleware. It deals with the exchange of messages in a communication network. The addressing scheme of this type of middleware is no longer of the point-to-point type, but is a message-oriented addressing scheme. The best known is the publish-subscribe paradigm shown here. Celery supports many types of message brokers, the most complete of which are RabbitMQ and Redis. To install Celery, we use the pip installer. In command prompts, just type the following. After this, we must install the message broker. There are several choices available for us to do this, but in our examples, we use RabbitMQ, which is a message-oriented middleware, also called broker messaging, that implements the Advanced Message Queuing Protocol, or AMQP. The RabbitMQ server is written in Erlang and is based on the Open Telecom Platform, or OTP, framework for the management of clustering and failover. To install RabbitMQ, download and run Erlang with the help of this link. We can then just download and run the RabbitMQ installer using this link. It takes a few minutes to download and we'll set up RabbitMQ and run it as a service with a default configuration. Finally, we install Flower, which is a web-based tool used to monitor tasks, running progress, task details, and graphs and stats. Use this link. To install it, just type this command from command prompt. Then we can verify the Celery installation. In command prompt, just type this. After this, the text should appear. For more complete details about the Celery installation procedure, you can visit this website. Awesome! We now know how to use Celery to distribute tasks. In our upcoming video, we'll see how to create a task with Celery. In our previous video, we saw the use of Celery to distribute tasks. Here's the second video of the section, Creating a Task with Celery. In this video, we'll see how to create a Celery application instance, and then we'll introduce the task. We'll show you how to create and call a task using the Celery module. Celery provides these methods that make a call to a task. 1. This task sends a task message. 2. This is a shortcut to send a task message, but does not support execution options. The delay method is better to use because it can be called as a regular function. For that, we use this. While using apply async, you should write this. To perform this simple task, we implement these two simple scripts. First is addTaskMain.py, and second is addTask.py. We must note again that the RabbitMQ service starts automatically on our server upon installation, so to execute the Celery worker server, we simply type these commands in the command prompt as shown. The output is shown in the first command prompt. Let's note the warnings in the output to disable Pickle as a serializer for security concerns. The default serialization format is Pickle simply because it is convenient. It supports the task of sending complex Python objects as task arguments. Whether you use Pickle or not, you may want to turn off this warning by setting the Celery accept content configuration variable. For reference, take a look at this web page. Now we launch the addTaskMain script from a second command prompt in order to run the Python file as shown. Finally, the result from the first command prompt should be like this. The result is 10. You can read it in the last line, as we expected. Let's focus on the first script, addTask.py. In the first two lines of code, we create a Celery application instance that uses the RabbitMQ service add broker. The first argument in the Celery function is the name of the current module, addTask.py. And the second argument is the broker keyboard argument, which indicates the URL used to connect the broker, RabbitMQ. Then we introduce the task. Each task must be added with the annotation, or decorator, which is @app.task. The decorator helps Celery to identify which functions can be scheduled in the task queue. After the decorator, we create the task that the workers can execute. Our first task will be a simple function that performs the sum of two numbers as shown. In the second script, addTaskMain.py, we call our task by using the delay method. Let's remember that this method is a shortcut to the apply a sync method, which gives us greater control of the task execution. If RabbitMQ operates under its default configuration, Celery can connect with no other information other than AMQP://scheme. Nice! So now we saw how to create a task using Celery. In our next video, we take a look at scientific computing with Scoop. In our previous video, we saw how to create a task with Celery. Here's the third video, titled Scientific Computing with Scoop. Scalable Concurrent Operations in Python, or Scoop, is a Python module to distribute concurrent tasks, called futures, on heterogeneous computational nodes. Its architecture is based on the ZeroMQ package, which provides a way to manage futures between the distributed systems. The main application of Scoop resides in scientific computing that requires the execution of many distributed tasks using all the computational resources available. To distribute its futures, Scoop uses a variation of the broker patterns. The central element of the communication system is the broker that interacts with all the independent workers to dispatch messages between them. The futures are created in the worker elements instead of the central node, the broker, with a centralized serialization procedure. This makes the topology architecture more reliable and makes performance better. In fact, the broker's main workload consists of networking and interprocess I/O between workers with relatively low CPU processing time. The Scoop module is available at this GitHub link, and its software dependencies are as follows. 1. Python, greater than or equal to 2.6 or greater than or equal to 3.2. 2. Distribute, greater than or equal to 0.6.2 or setup tools greater than or equal to 0.7. 3. Greenlet, greater than or equal to 0.3.4. 4. PyZMQ, greater than or equal to 13.1.0, and LIBZMQ, greater than or equal to 3.2.0. 5. SSH for remote execution. Scoop can be installed on Linux, Mac, and Windows machines. Like Disco, its remote usage requires an SSH software, and it must be enabled as a passwordless authentication between every computing node. For a complete reference about the Scoop installation procedure, you can read the information guide at the web page shown. On a Windows machine, you can install Scoop simply by typing this command: pip install Scoop. Otherwise, you can type the command python setup.py install from Scoop's distribution directory. Scoop is a library full of functionality that is primarily used in scientific computing problems. Among the methods used to find a solution to these problems that are computationally expensive, there is the Monte Carlo algorithm. In this example, we want to show you how to parallelize a Monte Carlo method for the solution of the following problem, the calculation of the number pi, using the features of Scoop. So, let's consider this code. To run a Scoop program, you must open Command Prompt and navigate to your working directory. Type and run this command. It might take some time to load the output. For our script, we'll expect output like this. The correct value of pi becomes more precise as we increase the number of attempts and workers. For 1,000 number of workers, value of pi becomes 3.140456. For 2,000 workers, value of pi becomes 3.142064. For 3,000 workers, value of pi becomes 3.14166. The code presented in this section is just one of the many implementations of the Monte Carlo method for the calculation of pi. The evaluate points in circle function is taken randomly and then given a point of coordinates, x and y, and then it's determined whether or not this point falls within the circle of the unit area. Whenever the points fallen in unit disk condition is verified, the variable is incremented. When the inner loop of the function ends, it'll present the total number of points falling within the circle. This number is sufficient to calculate the value of pi. In fact, the probability that the point falls within the circumference is pi/4. That's the ratio between the area of the unit circle equal to pi and the area of the circumscribed square equal to 4. So, by calculating the ratio between the number of points fallen inside the disk, task result, and the number of shots made, workers' attempts, you obtain an approximation of pi/4 and of course also of the number pi. The Scoop function is as shown. This takes care of distributing the computational load between the available workers and at the same time collects all the results. It executes evaluate points in circle in an asynchronous way and makes several calls to evaluate points in circle concurrently. Awesome! So in this video we saw how to carry out scientific computing with Scoop. In our next video we'll see how to handle map functions with Scoop. In the previous video we performed scientific computing with Scoop. This is the fourth video, titled Handling Map Functions with Scoop. In this video we compare the Scoop implementation of the MapReduce function with a serial implementation. A common task that is very useful when dealing with lists or other sequences of data is to apply the same operation to each element of the list and then collect the result. For example, a list update may be done in the following way from the Python idle. This is a common operation. However, Python has a built-in feature that does most of the work. The Python function map, a function, a sequence, applies a passed-in function to each item in an iterable object and returns a list containing all the function call results. Now, the same example would be here we pass in the map function the user-defined function multiply for 2. It's applied to each item in the items list, and finally we collect the result in a new list that is printed. A function defined and called without being bound to an identifier as an argument instead of a function. The same example now becomes the map built-in function has performance benefits because it's faster than a manually coded for loop. The Scoop Python modules define more than one map function that allow asynchronous computation that could be propagated to its workers. These functions are 1. Futures.map. This returns a generator that iterates the results in the same order as its inputs. It can thus act as a parallel substitute for the standard Python map function. 2. Futures.map as completed. This will yield results as soon as they are made available. 3. Futures.scoop.futures.MapReduce. This allows us to parallelize a reduction function after we apply the map function. It returns a single element. As mentioned earlier, we need to compare the MapReduce version of Scoop with its serial implementation. For that, we'll use this code. This will be the desired output. To evaluate the script, you must type this command in your command prompt. In this example, we compare the Scoop implementation of the MapReduce function with the serial implementation. The core of the script is the compare MapReduce function that contains the two implementations. Also in this function, we evaluate the execution time according to this schema. Then, in the output, we report the resulting time as shown here. To obtain the comparable execution time, we simulate a computational workload that introduces a time.sleep statement in the simulated word load function, which is shown here. The Scoop implementation of MapReduce is as shown here. The Futures MapReduce function has the following arguments. 1. Simulate work. This will be called to execute the futures. We also need to remember that a callable must return a value. 2. Operator.add. This will be called to reduce the futures results. However, it also must support two parameters and return a single value. 3. List. This is the iterable object that will be passed to the callable object as a separate future. The serial implementation of MapReduce is done using this code. The Python standard map function has two arguments, the simulate workload function and the list function iterable object. However, to reduce the result, we use the Python function sum. Amazing! In our next video, we'll see how to carry out remote method invocation with Pyro 4. In the previous video, we saw how to handle map functions with Scoop. This is the fifth video titled Remote Method Invocation with Pyro 4. In this video, we'll use Python scripts to build and use a simple client-server communication with the help of Pyro 4 middleware. Python Remote Objects, or Pyro 4, is a library that resembles Java's Remote Method Invocation, or RMI, which allows you to invoke a method of remote object that belongs to a different process and is potentially on a different machine, almost as if the object were local. That is, it belongs to the same process in which it runs the invocation. In this sense, the remote method invocation technology can be traced from a conceptual point of view. The idea of a remote procedure call, RPC, is reformulated for the object-oriented paradigm, in which, of course, the procedures are replaced by methods. The use of a mechanism for remote method invocation is an object-oriented system entails the significant advantages of uniformity and symmetry in the project, since it allows us to model the interactions between distributed processes using the same conceptual tool that is used to represent the interactions between the different objects of an application or the method call. As you can see from the preceding figure, Pyro 4 allows us to manage and distribute objects in the client-server style. This means that the main parts of a Pyro 4 system may switch from a client called to a remote object to an object called to serve a function. It's important to note that during the remote calling, there are always two distinct parts that a client and server accepts and executes the client call. Finally, the entire management of this mechanism is provided by Pyro 4 in a distributed way. The installation procedure is quite simple with the pip installer. From your command shell, type this. Otherwise, you can download the complete package from this link and install the package with the python setup.py install command from the package directory. For our examples, we'll use a Python 3.3 distro on a Windows machine. We'll now see how to build and use a simple client-server communication using the Pyro 4 middleware. So, we must have two Python scripts. This is the code for the server, server.py. The code for the client, client.py, is as shown. The server contains the object, the server class, that can be accessed remotely. In our example, this object only has the welcome message method that returns a string with a name inserted in the client session. To start the server, the start server function, we must follow some simple steps. 1. Build the instance, named server, of the server class using this command. 2. Make a Pyro daemon using this command. Pyro 4 uses daemon objects to dispatch incoming calls to appropriate objects. A server must create one daemon that manages everything from its instance. Each server has a daemon that knows about all the Pyro objects that the server provides. 3. To execute this script, we have to run a Pyro name server. So, we have to locate this name server that runs using this command. 4. Then we need to register the server as Pyro object. It'll be known only inside the Pyro daemon using this command. It returns the URI for the registered object. 5. Finally, we can register the object server with a name in the name server with this command. 6. The function ends with a call to daemon's event loop method. It starts the event loop of the server and waits for calls. The Pyro 4 API enables the developer to distribute objects in a transparent way. Our client scripts send the request to the server program to execute the welcome message method. The remote call is performed first by creating a proxy object with this command. In fact, Pyro 4 clients use proxy objects to forward method calls to the remote objects and pass results back to the calling code. Now we'll call the server's method that prints a welcome message. To run the example, we need a Pyro name server running. To do this, you can type this command in command prompt. After this, you'll see this message. This means that the name server is running in your network. Then you can start the server and the client scripts in two separate console windows. To run the server, just type the command as shown. Now you'll see something similar to what is shown. To run the client, just type this. After this, a message as shown on screen will appear. After the correct insertion, you must insert the name of the Pyro 4 server, that is, Pyro name server. You'll see this message asking you to type your name. Finally, you'll see a welcome message. Hi, welcome Sonali, as shown on screen. Nice! So in this video, we saw remote method invocation with Pyro 4. In our next video, we'll see how to chain objects with Pyro 4. In the previous video, we saw remote method invocation with Pyro 4. This is the sixth video, titled Chaining Objects with Pyro 4, which can be easily extended to handle more complex distributed architectures. In this video, we'll show you how to create a chain of objects, which call each other with Pyro 4. Let's suppose that we want to build a distributed architecture as shown. We have 4 objects, a client and 3 servers disposed in a chain topology as shown in the figure. The client forwards a request to server 1 and starts the chain call, forwarding the request to server 2. Then it calls the next object in the chain in server 3. The chain call ends when server 3 calls server 1 again. The example we're going to show highlights the aspects of the management of remote objects, which can be easily extended to handle the more complex distributed architectures. To implement a chain of objects with Pyro 4, we need 5 Python scripts as shown. The first one is the client, client.py. Here's the code for it. Each server will be characterized by this parameter, which identifies it in the chain, and the parameter next, which defines the next server that is subsequent to this in the chain. For a visualization of the implemented chain, you can see the figure associated with this video. The last script is the chain object. This is the code for it. The core of this example is the chain class that we defined in the chain topology.py script. It allows communication between the 3 servers. In fact, each server calls the class to find out which is the next element of the chain, referred to the method process in chain topology.py. Also, it executes the call with the pyro4.core.proxy statement, which is this. If the chain is closed, the last call is done from server 3 to server 1, a closing message is printed out using this command. A forwarding message is printed out if there is a next element in the chain using this command. The code for the server is the same and only differs on the definition of the current element and the next element of the chain. For example, this is the definition for the first server. The remaining lines of the code define in the same manner as the previous example the communication with the next element in the chain. Finally, in the client script, we start the process by calling the first element, server 1, in the chain. To execute this example, start by running the Pyro 4 name server as shown. Then run the 3 servers. In 3 separate command prompts, type the Python server _name.py command. A message like this should appear after this for server 1. For server 2, something similar to what is shown on screen will appear. A message similar to what is shown should appear for server 3. Finally, you must run the client.py script from another command shell. The message here shows as a result the forwarding request passed across the 3 servers. When it comes back to server 1, the task is completed. Also, here we can focus on the behavior of the object servers when the request is forwarded to the next object in the chain. To see what happens next, refer to the message below the start message in the following script for server 1. The result of server 2 is as shown. The results of server 3 will appear like this. Brilliant! We just saw how to chain the objects with Pyro 4. In our next video, we'll develop a client-server application with Pyro 4. In the previous video, we saw how to chain objects. This is the 7th video, developing a client-server application with Pyro 4. In this video, we'll run 3 scripts, one for the client object, second one for the shop object, and the third one for the server object. In this video, we'll show you how to build a simple client-server application with Pyro 4. The application that we'll show here is not complete, but is equipped with all the methods that will successfully complete and improve it. A client-server application indicates a network architecture in which, generally, a client computer or terminal connects to a server for the use of a certain service, such as the sharing of a certain resource, hardware, or software with other clients and relying on the underlying protocol architecture. In our system, the server manages an online shopping site, while the client manages the customers that are registered on the site and connect to it for shopping. For the sake of simplicity, we have 3 scripts. The first one represents the object client in which we have customer management. The second script is the object shop, and the third script is the object server. For the server, server.py, the code is this. The code for the client, client.py, is as shown. This is the code for the object shop, or shop.py. The server side of the application must locate the shop function object calling the statement using this code. Then it must enable a communication channel using this code. The shop.py script contains classes for account and shop management. The shop class manages each account. It provides methods to log in and log out, manage customers' money, and to buy items. Each customer has their own account object that provides methods for customer deposit management. This is the code for that. Finally, the client.py script contains the class that is used to start the simulation. In the main program, we instantiate two customers, Rashmi and Mita, as you can see here. They deposit some cash in on the site and then start with their shopping as shown. Rashmi buys a book. This is the code for that. Mita twice deposits $100 in her account. This is the code we use. At the end of the simulation, the main program reports the counts deposit of Mita and Rashmi with the help of this code. To execute the code, you first must enable the Pyro4 name server using this code. Then start the server by using the python server.py command. A shell, like the one shown on the screen, will appear when you do this. Finally, you should start the customer simulation with the following command. The shown text will be printed out with the use of this command. This output shows a simple session for two customers, Mita and Rashmi. Wonderful! In this video, we saw how to develop a client-server application with Pyro4. In our next video, we'll see how to communicate sequential processes with PyCSP. In the previous video, we developed a client-server application with Pyro4. This is the 8th video, Communicating Sequential Processes with PyCSP. In this video, we'll introduce the basic concepts of PyCSP, the processes, and the channels. PyCSP is a Python module based on communicating sequential processes, which is a programming paradigm developed to build concurrent programs via message passing. The PyCSP module is characterized by 1. The exchange of messages between processes. 2. The probability of using a thread to use shared memory. 3. The exchange of messages is done through channels. The channels allow 1. An exchange of values between processes. 2. The synchronization of processes. PyCSP allows the use of different channel types, one-to-one, one-to-any, any-to-one, and any-to-any. These names indicate the number of writers and readers that can communicate over the channel. For our examples, we'll use the Python version 2.7. In this first example, we want to introduce the basic concepts of PyCSP, the processes, and channels. So, we have defined two processes named counter and printer. We now want to see how to define the communication between these processes. Let's consider this code. To execute this code, simply press the Run button on the Python 2.7 idle. An output like this will be shown shortly after this. In this example, we use the functions defined in the pycsp.parallel module as shown. This module has the any-to-any channel type, which allows multiple processes, which are attached to the ends of the channels, to communicate through it. To create the channel A, we use this statement. This new channel is automatically hosted in the current Python interpreter. For each Python interpreter that imports the pycsp.parallel module, only a port that handles all the channels started in the Python interpreter will be listed. However, this module does not provide a name server available for the channels. So, to connect to a hosted channel, you must know the right location. For example, to connect the channel B to the local host port 8888, we input this code. In pycsp, we have three basic ways to manage a channel. 1. Channel.disconnect method. This allows the Python interpreter to quit. It's used in a client-server setting where a client wants to be disconnected after it receives a reply from a server. 2. Channel.reader method. This creates and returns the reader end of the channel. 3. Channel.writer method. This creates and returns the writer end of the channel. pycsp can be installed using the pip installer via the following command. Also, it's possible to download the entire distribution from GitHub. Download it and then type this from the installation directory. To indicate a process, we use the @process decorator. In pycsp, each generated CSP process is implemented as a single OS thread. In the example shown, we have two processes, a counter and a printer. The process counter has two arguments, cout to redirect its output and limit, which defines the total number of items to be printed. The poison statement, poison cout, means that the channel end is poisoned. This means that all subsequent reads and writes on this channel will throw an exception that can be used to end the current procedure or disconnect the channel. We also note that the poisoning may cause a race condition if there are multiple concurrent procedures. The process printer only has one argument, which is the item to print, defined in the cin variable. The core of the script is this code. This defines the A channel, which permits communication between the two processes. Finally, the parallel statement is as highlighted. This starts all the processes and blocks them only if the counter and process have terminated communication with each other. This statement represents the basic idea of CSP, that is, concurrent processes synchronize with each other by synchronizing their I/O through the channel A. The way to do this is to allow I/O to occur only when a process counter states that it is ready to output to a process printer specifically and the process printer states that it's ready to input from a process counter. If one of these happens without the other being true, the process is put in a wait queue until the other process is ready. Each pycsp application creates a server thread to manage the incoming communication over the channels. So, it's always necessary to terminate each pycsp application with a call to the shutdown method. pycsp provides two methods to trace its execution. 1. Trace init. This is used to start the trace. 2. Trace quit. This is used to stop the trace. These must be placed in the schema. CSP is a formal language used to describe the interactions of concurrent processes. It falls under the mathematical theory of competition, which is known as algebra processes. It's been used in practice as a tool for the specification and verification of the competition aspects of a wide variety of systems. The rules of the CSP-inspired programming language Occam are now widely used as a parallel programming language. For those of you who are interested in CSP's theory, we suggest that you go through Hoare's original book, which is available online at this link. We suggest you go through Hoare's original book, which is available online at this link. Nice! So in this video, we saw how to communicate sequential processes with PyCSP. In our next video, we'll see how to use MapReduce with Disco. In our previous video, we saw how to use MapReduce with Disco. This is a remote procedure call with RPYC. In this video, to carry out the remote procedure call with RPYC, we'll first run a client that connects to the server. Next, we'll see how to execute the print statement on the server. Remote Python Call, RPYC, is a Python module that is used for remote procedure calls as well as for distributed computing. The idea at the base of RPC is to provide a mechanism to transfer control from a program or client to another server, similar to what happens with the invocation of a subroutine in a centralized program. The advantages of this approach are that it has very simple semantics and knowledge of familiarity of the centralized mechanism of a function call. In a procedure invocation, the client process is suspended until the process server has performed the necessary computations and is given the results of computations. The effectiveness of this method is due to the fact that the client-server communication takes the form of a procedure call instead of invocations to the transport layer, so that all the details of the operation of the network are hidden from the application program by placing them in local procedures called stubs. The main features of RPYC are: 1. In syntactic transparency, a remote procedure call can have the same syntax as a local call. 2. In semantic transparency, a remote procedure call is semantically equivalent to the local one. 3. Handling synchronous and asynchronous communication. 4. Symmetric communication protocol means that both the client and server can serve a request. The installation procedure is quite simple with the pip installer. Otherwise, you can go to this GitHub link and download the complete package. It's a zip file. Finally, to install RPYC, you must type the command as shown: python setup.py install from the package directory. After the installation, you can just explore this library. In our examples, we'll run a client and server on the same machine, localhost. We're now ready for the first example that shows you how to redirect std out of a remote process. This is the code used. By running this script, you'll see the redirected output in the server side as shown. The first step is to run a client that connects to the server. This is the command used. Here, the client-side statement rpyc.classic.connect host port creates a socket connection to the given host and port. Sockets define the endpoint of a connection. RPYC uses sockets to communicate with other programs, which may be distributed on different computers. Next, we have this statement. This executes the print statement on a server, a remote exec statement. Awesome! So we have successfully carried out the remote procedure call with RPYC. So here we are at the end of this section. In this section, we saw how to use Celery to distribute tasks and to create tasks. We then carried out scientific computing and saw how to handle map functions with the help of Scoop. Furthermore, we moved on to understand remote method invocation and chaining objects with Pyro 4. We also saw how to develop a client-server application and communicate sequential processes with Pyro 4. In the end, we learned how to carry out a remote procedure call with RPYC. In our next section, we'll take a look at GPU programming with Python. Our previous section introduced us to distributed computing. Welcome to the sixth section of the course, titled GPU Programming with Python. This section will teach you how to exploit the computing power provided by the GPU cards, using the powerful Python modules which are PyCUDA, Numba Pro, and PyOpenLCL. Let's get started with our first video, using the PyCUDA module. In this video, we'll first take a look at a hybrid programming model, and further we'll understand the kernel and thread hierarchy. The aim of this video is basically to show how to use PyCUDA module. PyCUDA is a Python wrap for Compute Unified Device Architecture, or CUDA, the software library developed by NVIDIA for GPU programming. The CUDA programming model is the starting point of understanding how to program the GPU properly with PyCUDA. There are concepts that must be understood and assimilated to be able to approach this tool correctly and to understand the more specific topics that are covered in the upcoming videos. Let's take a look at a hybrid programming model. The programming model hybrid of CUDA and consequently of PyCUDA, which is a Python wrapper, is implemented through specific extensions to the standard library of the C language. These extensions have been created whenever possible syntactically like the function calls in the standard C library. This allows a relatively simple approach to a hybrid programming model that includes the host and device code. The management of the two logical parts is done by the NVCC compiler. Here's a brief description of how this compiler works. 1. It separates a device code from a host code device. 2. It invokes a default compiler, for example GCC, to compile the host code. 3. It builds the device code in the binary form, or Cuban objects, or in the form assembly, code PTX. 4. It generates a host key global that also includes code PTX. The compiled CUDA code is converted to a device-specific binary by the driver during runtime. All the steps of compilation mentioned earlier are executed by PyCUDA at runtime, which makes it a just-in-time, or JIT, compiler. The drawback of this approach is the increased load time of the application, which is the only way to maintain compatibility forward. That is, you can perform operations on a device that does not exist at the time of the actual compilation. A JIT compilation therefore makes an application compatible with future devices that are built on architectures with higher computing power, so it's not yet possible to generate any binary code. Now let's take a look at the kernel and thread hierarchy. An important element of the CUDA program is the kernel. It represents the code that is executed in parallel on the basis of specifications that will be clarified later with the examples described here. Each kernel's execution is done by computing units that are called threads. Unlike threads in CPU, GPU threads are lighter in such a way that the change of context is not one of the factors to be taken into account in a code performance evaluation, because it can be considered as instantaneous. To determine the number of threads that must perform a single kernel in their logical organization, CUDA defines a two-level hierarchy as shown in this figure. In the highest level, it defines a so-called grid of blocks. This grid represents a bidimensional structure where the thread blocks are distributed, which are three-dimensional. Based on this structure, a kernel function must be launched with additional parameters that specify precisely the size of the grid and block. On this wiki page, the basic instructions to install PyCUDA on the main operative systems, Linux, Mac, and Windows, are explained. With these instructions, you'll build a 32-bit PyCUDA library for a Python 2.7 distro. The first step is to download and install all the components provided by NVIDIA to develop CUDA. Refer to this link for all the available versions. These components are 1. The CUDA toolkit, which is available at this link. 2. The NVIDIA CUDA development driver is available at this link. 3. The NVIDIA GPU Computing SDK is available at this link. Download and install NumPy for 32-bit Python 2.7 and Visual Studio C++ 2008 Express, and be sure to set all the system variables. Open the file msvc9compiler.py located at this path. After this line, add the new line as shown. Download PyCUDA from this web link. Open Visual Studio 2008 command prompt and follow the given steps. 1. Go in the PyCUDA directory. 2. Execute python-configure.py. 3. Edit the created file siteconfig.py. Finally, install PyCUDA with the following commands in VS 2008 command prompt. The present example has a dual function. The first is to verify that PyCUDA is properly installed, and the second is to read and print the characteristics of the GPU cards. After running the code, we should have an output like this. The execution is pretty simple. In the first line of code, PyCUDA.driver is imported and then initialized as shown. The PyCUDA driver module exposes the driver level to the programming interface of CUDA, which is more flexible than the CUDA C runtime level programming interface, and it has a few features that are not present at runtime. Then, it cycles into drv.device.count method, and for each GPU card found, the name of the cards and main characteristics, computing capability and total memory, are printed. PyCUDA is developed by Andreas Glockner. You can refer to this link for more information. For any other information concerning PyCUDA, you can refer to this link. Nice! In this video, we saw how to use PyCUDA module. In our next video, we'll see how to build a PyCUDA application. So, in the previous video, we saw how to use the PyCUDA module. This is the second video titled Building a PyCUDA Application. In this video, we'll first create an array on CPU and transfer it to GPU. We'll further perform a task on the array in the GPU. Then, we'll transfer the array from GPU to the CPU. Finally, we'll print the results. The PyCUDA programming model is designed for the common execution of a program on a CPU and GPU, so as to allow you to perform the sequential parts on the CPU and the numeric parts, which are more intensive on the GPU. The phases to be performed in the sequential mode are implemented and executed on the CPU, or the host, while the steps to be performed in parallel are implemented and executed on the GPU, or the device. The functions to be performed in parallel on the device are called kernels. As you can see here in the diagram, the steps to execute a generic function kernel on the device are as follows. 1. The first step is to allocate the memory on the device. 2. Then we need to transfer data from the host memory to that allocated on the device. 3. Next, we need to run the device, run the configuration, and invoke the kernel function. 4. Then we need to transfer the results from the memory on the device to the host memory. 5. Finally, release the memory allocated on the device. To show the PyCUDA workflow, let's consider a 5x5 random array in this procedure. 1. Create the 5x5 array on the CPU. 2. Transfer the array to the GPU. 3. Perform a task on the array in the GPU. Double all the items in the array. 4. Transfer the array from the GPU to the CPU. 5. Print the results. The example output should be like this. This code starts with the imports, as you can see here. The import PyCUDA auto init statement automatically picks a GPU to run based on its availability and number. It also creates a GPU context for the subsequent code to run. If needed, both the chosen device and the created context are available from the PyCUDA auto init as importable symbols, whereas the source module component is the object where a C-like code for the GPU must be written. The first step is to generate the input 5x5 matrix. Since most GPU computations involve large arrays of data, the NumPy module must be imported. Then, the items in the matrix are converted into a single precision mode. Many NVIDIA cards support only a single precision using this code. The first operation that needs to be done in order to implement a GPU is to load the input array from the host memory, CPU, to the device, GPU. This is done at the beginning of the operation and consists of two steps that are performed by invoking two functions provided by PyCUDA. The memory allocation on the device is performed via the function CUDA.memAlloc. The device and host memory may not ever communicate while performing a function kernel. This means that to run a function parallel on the device, the data related to it must be present in the memory of the device itself. Before you copy data from the host memory to the device memory, you must allocate the memory required on the device using this command. Now copy the matrix from the host memory to that of the device with the help of these functions. Also note that a GPU is one-dimensional, and on the device we need to handle it as such. All these operations don't require the invocation of a kernel and are made directly by the main processor. The source module entity serves to define the C-like kernel function double matrix that multiplies each array entry by 2. The global qualifier directive indicates that the function double matrix will be processed on the device. Only the CUDA NVCC compiler will perform this task. Let's take a look at the function's body. The IDX parameter is the matrix index identified by the thread coordinates thread_id_x and thread_id_x.y. Then the element matrix with the index IDX is multiplied by 2. Note that this kernel function will be executed once in 16 different threads as shown in the diagram. Both the variables thread_id_x and thread_id_x.y contain indices between 0 and 3, and the pair is different for each thread. Thread scheduling is directly linked to the GPU architecture and its intrinsic parallelism. A block of threads is assigned to a single streaming multiprocessor, or SM, and the threads are further divided into groups called warps. The size of a warp depends on the architecture under consideration. The threads of the same warp are managed by the control unit called the warp scheduler. To take full advantage of the inherent parallelism of SM, the threads of the same warp must execute the same instruction. If this condition doesn't occur, we speak of the divergence of threads. If the same warp threads execute different instructions, the control unit cannot handle all the warps. It must follow the sequences of instructions for every single thread, or for homogeneous subsets of threads, in a serial mode. Let's observe how the thread block is divided into various warps. Threads are divided by the value of thread IDX. The thread IDX structure consists of 3 fields: thread IDX.x, thread IDX.y, and thread IDX.z. We can see that the code in the kernel function will be automatically compiled by the NVCC CUDA compiler. If there are no errors, the pointer of this compiled function will be created. In fact, mod get function, double matrix, returns an identifier to the function that we created. To perform a function on the device, you must first configure the execution appropriately. This means that you need to determine the size of the coordinates to identify and distinguish the thread belonging to different blocks. This will be done using the block parameter inside the func call. The block equals 551 function tells us that we are calling a kernel function with the AGPU linearized input matrix and a single thread block of the size 5 threads in the X direction, 5 threads in the Y direction, and 1 thread in the Z direction, 16 threads in total. This structure is designed with the parallel implementation of the algorithm in mind. The division of the workload results in an early form of parallelism that is sufficient and necessary to make use of the computing resources provided by the GPU. Once you've configured the kernel's invocation, you can invoke the kernel function that executes instructions parallel on the device. Each thread executes the same code kernel. After the computation in the GPU device, we use an array to store the results using this code. This will be printed using this code. A warp executes one common instruction at a time. So, to maximize the efficiency of the structure, all must agree with the same thread's path of execution. When more than one thread block is assigned to a multiprocessor to run, they are partitioned into warps that are scheduled by a component called the warp scheduler. Wonderful! So, in this video we saw how to build a PyCUDA application. In our next video, we'll understand the PyCUDA memory model with matrix manipulation. In our previous video, we saw how to build PyCUDA applications. Welcome to the third video of this section, Understanding the PyCUDA Memory Model with Matrix Manipulation. In this video, we'll first prepare the input matrix and the output matrix. We'll then transfer matrices in the GPU device with the PyCUDA function. In the end, we'll verify whether the computation is correct. A PyCUDA program, to make the most of available resources, should respect the rules dictated by the structure and the internal organization of the SM that imposes constraints on the performance of the thread. In particular, the knowledge and the correct use of the various types of memory that the GPU makes available is fundamental in order to achieve maximum efficiency in the programs. In the CUDA-capable GPU card, there are 4 types of memories, which are defined as 1. Registers. In this, a register is allocated for each thread. This can only access its register but not the registers of other threads, even if they belong to the same block. 2. The shared memory. Here, each block has its own shared memory between the threads that belong to it. Even this memory is extremely fast. 3. The constant memory. All threads in a grid have constant access to the memory, but can be accessed only while reading. The data present in it persists for the entire duration of the application. 4. The global memory. All threads of all the grids, so all kernels, have access to the global memory. The constant memory data present in it persists for the entire duration of the application. This is the GPU memory model. One of the key points to understand how to make the PyCUDA programs with satisfactory performance is that not all memory is the same, but you have to try to make the best of each type of memory. The basic idea is to minimize the global memory access via the use of shared memory. The technique is usually used to divide the domain/codomain of the problem in such a way that we enable a block of threads to perform its elaborations in a closed subset of data. In this way, the threads adhering to the concerned block will work together to load the shared global memory area that is to be processed in the memory, to then proceed to exploiting the higher speed of this memory zone. The basic steps to be performed for each thread will then be as follows. 1. Load data from the global memory to the shared memory. 2. Synchronize all the threads of the block so that everyone can read safety position shared memory filed by other threads. 3. Process the data of the shared memory. 4. Make a new synchronization as necessary to ensure that the shared memory has been updated with the results. 5. Write the results in the global memory. To better understand this technique, we'll present an example which will clarify this approach. This example is based on the product of 2 matrices. The previous figure shows the product of matrices in the standard way and the corresponding sequential code to calculate where each element must be loaded from a row and a column of the matrix input. If each thread was entrusted with the task of calculating an element of the matrix, the memory accesses would dominate the execution time of the algorithm. What we can do is rely on a block of threads for the task of calculating a submatrix of output so that it's possible to reuse the data loaded from the global memory and to collaborate threads in order to minimize the memory accesses for each of them. This example shows this technique. The example output will be as shown. Let's consider the PyCUDA programming workflow. First of all, we must prepare the input matrix and the output matrix to store the results. We do this using this code. Then, we transfer these matrices in the GPU device with the PyCUDA function GPUArray2GPU method. We use this code for that. The core of the algorithm is the kernel function. Note that the global keyword specifies that this function is a kernel function and it must be called from a host to generate the thread hierarchy on the device. The thread ID x.x and thread ID y.y are the thread indexes in the grid. We also note again that all these threads execute the same kernel code, so different threads will have different values with different thread coordinates. In this parallel version, the loop variables I and j of the sequential versions are now replaced with thread ID x.x and thread ID x.y. The loop iteration through these indexes is simply replaced by these thread indexes, so in the parallel version, we have only one loop iteration. When the kernel matrix mul kernel is invoked, it's executed as a grid of the size 5 into 5 of parallel threads using this code. Each CUDA thread grid typically comprises of thousands to millions of lightweight GPU threads per kernel invocation. Creating enough threads to fully utilize the hardware often requires a large amount of data parallelism. For example, each element of a large array might be computed in a separate thread. Finally, we print out the results to verify that the computation is okay and report the differences between the C CPU and C GPU matrix products. Great! So we just saw the PyCUDA memory model with matrix manipulation. In our next video, we'll cover kernel invocations with GPU array. In the previous video, we took a look at the PyCUDA memory model with matrix manipulation. This is the fourth video of this section, titled Kernel Invocations with GPU Array. In this video, we'll import the modules and perform the computation in the GPU. In the previous video, we saw how to invoke a kernel function using this class. It creates a module from the CUDA source code called kernel source. Then, the NVIDIA NVCC compiler is invoked with options to compile the code. However, PyCUDA introduces the class PyCUDA GPUArray.GPUArray that provides a high-level interface to perform calculations with CUDA, which looks like this. This works in a similar way to numpy.ndArray, which stores its data and performs its computations on the compute device. The shape and d-type arguments work exactly as in NumPy. All the arithmetic methods in GPU array support the broadcasting of scalars. The creation of GPU array is quite easy. One way is to create a NumPy array and convert it, as shown in the following code. You can print GPU array as you do normally. The following example represents not only an easy introduction, but also a common use case of GPU computations, perhaps in the form of an auxiliary step between other calculations. The script for this is as shown. The output is running the function from Python idle, as shown here. Of course, we have to import all the required modules. The AGPU input matrix contains all the items that are generated randomly. To perform the computation in the GPU, double all the items in the matrix, we have only one statement. The result is put in the A doubled matrix using the get method. Finally, the result is printed as here. The PyCUDA.GPU array supports all the arithmetic operators and a number of methods and functions, all patterned after corresponding functionality in NumPy. In addition to this, many special functions are available in PyCUDA.cu math. The arrays of approximately uniformly distributed random numbers may be generated using the functionality in PyCUDA.cu random. Nice! This video showed us how to invoke kernel with GPU array. In our next video, we'll evaluate the element-wise expressions with PyCUDA. In our previous video, we saw how to invoke kernel with GPU array. This is our fifth video, evaluating element-wise expressions with PyCUDA. In this video, we'll evaluate the linear combination of the vectors to use element-wise kernel call. The PyCUDA.elementwise.elementwise kernel function allows us to execute the kernel on complex expressions that are made of one or more operands into a single computational step, which is as shown here. Here, we note that 1. Arguments. This is a C-argument list of all the parameters that are involved in the kernel's execution. 2. Operation. This is the operation that is to be executed on the specified arguments. If the argument is a vector, each operation will be performed for each entry. 3. Name. This is the kernel's name. 4. Operational parameters. These are the compilation directives that are not used in the example which follows. In this example, we'll show you the typical use of the element-wise kernel call. We have two vectors of 50 elements, input vector A and input vector B, that are built in a random way. The task here is to evaluate their linear combination. The code for this is shown here. The output for this from command prompt is as follows. After the usual import, we note, from PyCUDA.elementwise import elementwise kernel. We must build all the elements that are to be manipulated. Let's remember that the task to be done is to evaluate a linear combination of two vectors, input vector A and input vector B. These two vectors are initialized using the PyCUDA.cu random library, which is used for the generation of pseudo-random numbers. To import the library, use the following code. To define the random vector, 50 elements, use this code. We defined the two coefficient of multiplication that are to be used in the calculation of linear combination of these two vectors using this code. The core example is the kernel invocation for which we use the PyCUDA element-wise kernel construct. This is the code used for that. The first line of the argument list in a C-style definition defines all the parameters to be inserted for the calculation. The second line defines how to manipulate the arguments list. For each value of the index I, a sum of these components must be evaluated. The last line gives the linear combination name to element-wise kernel. After the kernel, the resulting vector is defined. It's an empty vector of the same dimension as of the input vector. This is the code which is used. You can check the results using this code. The assert function tests the result and triggers an error if the condition is false. In addition to the CU random library derived from the CUDA library, PyCUDA provides other math libraries, so you can take a look at these libraries listed at this webpage. Amazing! Here we successfully evaluated element-wise expressions with PyCUDA. In our upcoming video, we'll take a look at the MapReduce operation with PyCUDA. In our previous video, we saw how to evaluate the element-wise expressions with PyCUDA. This is the sixth video of the section, the MapReduce operation with PyCUDA. In this video, we'll first define the inputs. We'll then define the MapReduce operation and invoke the kernel function. Further, we'll print the input vectors and the resulting dot product. PyCUDA provides a functionality to perform reduction operations on the GPU. This is possible with the PyCUDA reduction kernel method highlighted here. Here we note that 1. dtype out. This is the output's data type and must be specified by the numpy.dtype data type. 2. Arguments. This is a C argument list of all the parameters involved in the reductions operation. 3. Map expression. This is a string that represents the mapping operation. Each vector in this expression must be referenced with a variable I. 4. Reduce expression. This is a string that represents the reduction operation. The operands in this expression are indicated by lowercase letters such as A, B, C, up to Z. 5. Name. This is the name associated with the reduction kernel with which the kernel is compiled. 6. Operational parameters. These are not important in this recipe as they are the compiler's directives. The method executes a kernel on vector arguments, at least one, performs map expression on each entry of the vector argument, and then performs reduce expression on its outcome. This example shows the implementation of a dot product of two vectors, 500 elements, through an instantiation of the reduction kernel class. The dot product, or scalar product, is an algebraic operation that takes two equal-length sentences of numbers, usually coordinate vectors, and returns a single number that is the sum of the products of the corresponding entries of the two sequences of numbers. This is a typical MapReduce operation, where the map operation is an index-by-index product and the reduction operation is the sum of all the products. The PyCUDA code for this task is very short. Running the code from the command prompt, you'll have an output like this. In this script, the input vectors input vector A and input vector B are integer vectors. Each of them, as you can see from the preceding output result, ranges from 0 to 399 elements, 400 elements in total. After the definition of the inputs, we can define the MapReduce operation by calling the reduction kernel PyCUDA function. This kernel operation is defined as follows. 1. The first entry in the argument list tells us that the output will be an integer. 2. The second entry defines the data types for the inputs, array of integers, and has C-like notation. 3. The third entry is the map operation, which is the product of the ith element of the two vectors. 4. The fourth operation is the reduction operation, which is the sum of all the products. Observe that the end result of calling the reduction kernel instance is a GPU array scalar that still resides in the GPU. It can be brought to the CPU by a call to its get method or can be used in the place of the GPU. Then, the kernel function is invocated using this code. The input vectors and the resulting dot product are printed out as shown. Awesome! In this video, we saw how to carry out the MapReduce operation with PyCUDA. In our next video, we'll take a look at GPU programming with Numba Pro. Welcome to the 7th video of this section, GPU Programming with Numba Pro. In the previous video, we carried out the MapReduce operation with PyCUDA. In this video, we give a demonstration of the Numba Pro compiler using the annotation @gu vectorize. Numba Pro is a Python compiler that provides a CUDA-based API to write CUDA programs. It's designed for array-oriented computing tasks, much like the widely used NumPy library. The data parallelism in array-oriented computing tasks is a natural fit for accelerators such as GPUs. Numba Pro understands NumPy array types and uses them to generate efficient compiled code for execution on GPUs or multi-core CPUs. The compiler works by allowing you to specify type signatures for Python functions, which enable compilation at runtime, called the JIT compilation. The most important decorators are 1. NumbaPro.jit. This allows a developer to write CUDA-like functions. When encountered, the compiler translates the code under the decorator into the pseudo-assembly PTX language to be executed in the GPU. 2. NumbaPro.AutoJIT. This annotates a function for a deferred compilation procedure. This means that each function with this signature is compiled exactly once. 3. NumbaPro.Vectorize. This creates a so-called ufunc object, the NumPy universal function, that takes a function and executes it in parallel in vector arguments. 4. GUVectorize. This creates a so-called GUfunc object, the NumPy generalized universal function. A GUfunc object may operate on entire subarrays. All these decorators have a compiler directive called a target that selects the code generation target. The Numba Pro compiler supports the parallel and GPU targets. The parallel target is available to vectorize the operations, while the GPU directive offloads the computation to an NVIDIA CUDA GPU. Numba Pro is part of Anaconda Accelerate, which is a commercially licensed product. Numba Pro is also available under a free license for academic users from Continuum Analytics. It's built on top of the BSD-licensed open-source Numba project, which itself relies heavily on the capabilities of the LLVM compiler. The GPU backend of Numba Pro utilizes the LLVM-based NVIDIA compiler SDK. To get started with Numba Pro, the first step is to download and install the Anaconda Python distribution using this link. It's a completely free, enterprise-ready Python distribution for large-scale data processing, predictive analytics, and scientific computing. It includes many popular packages, NumPy, SciPy, Matplotlib, IPython, and so on, and Conda, which is a powerful package manager. Once you have Anaconda installed, you must type the following instructions from Anaconda's command prompt. Numba Pro does not ship the CUDA driver. It's the user's responsibility to ensure that their systems are using the latest drivers. After the installation, it's possible to perform the detection of the CUDA library in GPU, so let's open Python from the Anaconda console and type. The output of these two lines of code should be as follows. We used a 64-bit Anaconda distro. In this example, we give a demonstration of the Numba Pro compiler using the annotation @GUVectorize. In this task, we try to execute a matrix multiplication using the Numba Pro module. After running the code using the Anaconda console, we should have an output like this. The @GUVectorize annotation works on array arguments. This decorator takes an extra argument to specify the GUfunc signature. The arguments are explained as follows. 1. The first three arguments specify the types of data to be managed, which are the array of integers shown here. 2. The last argument of @GUVectorize specifies how to manipulate the matrix dimensions shown here. In the subsequent code, we define the matmul ABC operation. It accepts the two input matrix A and B and produces a C output matrix. According to the GUfunc signature, we should have this. The matrix product is simply performed via 3 for loops along with the matrix indices shown here. The NumPy's function radian is used to build integers from random matrices. Finally, the matmul function is called with these matrices with arguments, and the resultant matrix is printed out. Great! So in this video, we saw GPU programming with Numba Pro. In our next video, we'll see how to use GPU-accelerated libraries with Numba Pro. In the previous video, we saw GPU programming with Numba Pro. This is the 8th video, using GPU-accelerated libraries with Numba Pro. In this video, we'll first import libraries and define the matrix dimension along with input matrices. Further, we'll compare the calculation done with NumPy and QBLAS. Numba Pro provides a Python wrap for CUDA libraries for numerical computing. Each code using these libraries will get a significant speedup without writing any GPU-specific code. The libraries are explained as follows. 1. CU BLAS. This is a library developed by NVIDIA that provides the main functions of linear algebra to run on a GPU. Like the basic linear algebra subprograms, or BLAS, library that implements the functions of linear algebra on the CPU, the CU BLAS library classifies its functions into 3 levels. Level 1. Vector operations. Level 2. Transactions between a matrix and a vector. Level 3. Operations between matrices. The division of these functions into 3 levels is based on the number of nested loops that are needed to perform the selected operation. More precisely, the operations of the level are essential cycles that are geared to complete the execution of the selected function. 2. CU FFT. This provides a simple interface to calculate the fast Fourier transform, FFT, in a distributed manner on an NVIDIA GPU, enabling you to exploit the parallelism of the GPU without having to develop your own implementation of the FFT. 3. CU RAND. This library provides the creation of quasi-random numbers. A quasi-random number is a random number generated by a deterministic algorithm. 4. CU sparse. This provides a set of functions for the management of sparse matrices. Unlike the previous case, its functions are classified into 4 levels. Level 1. These are operations between a vector that is stored in a shed and a vector that is stored in a dense format. Level 2. These are the transactions between a matrix format stored in a shed and a vector stored in the dense format. Level 3. These are the operations in a matrix format that are stored in a shed and set of vectors that are stored in a dense format. This can be considered as one large dense matrix. Conversion. These are operations that allow the conversion between different storage formats. In this example, we present an implementation of General Matrix Multiply, or GEMM, which is a routine to perform matrix-to-matrix multiplication on NVIDIA GPUs. The sequential version using the NumPy Python module and the parallel version using the CU BLAS library will be reported. Also, a comparison of the execution time will be made between the 2 algorithms. The code for this is as shown. The output obtained for this will be as shown on screen. The result obtained confirms the effectiveness of the CU BLAS library. In order to make a comparison between a NumPy and a QBLAS implementation of a matrix product, we import all the required libraries using this. Also, we define the matrix dimension as 10. The core algorithm is the gem function shown here. First, we define the input matrices. Here, D will contain the output of the QBLAS implementation. In this example, we compare the calculation done with NumPy and QBLAS. The NumPy evaluation is E equals np dot dot A, B, where the matrix E will contain the dot product. Finally, the CU BLAS implementation is done using this code. The gem function is a QBLAS level 3 function shown here. It realizes a matrix-to-matrix multiplication in the form of C equals alpha times op A times op B plus beta times C, where op is transpose or not. At the end of the function, we compare the 2 results and report the execution time, CUDA time. In this example, we saw an application of the QBLAS library. For a more complete reference, refer to these 2 links for a complete list of CUDA function libraries wrapped with NUMBA Pro. Brilliant! So this video showed us how to use GPU-accelerated libraries with NUMBA Pro. In our next video, we'll see how to use the PyOpenCL module. Welcome to the 9th video, using the PyOpenCL module. In our previous video, we saw how to use GPU-accelerated libraries with NUMA Pro. In this video, we'll enumerate all major hardware features using the OpenCL library. Open Computing Language, or OpenCL, is a framework used to develop programs that work across heterogeneous platforms, which can be made either by the CPU or GPU that are produced by different manufacturers. This platform was created by Apple, but has been developed and maintained by a non-profit consortium called the Kronos Group. This framework is the main alternative for the CUDA execution of software on a GPU, but has a point of view that is diametrically opposed. However, CUDA makes specialization its strong point, produced, developed, and compatible with NVIDIA, ensuring excellent performance at the expense of portability. OpenCL offers a solution compatible with nearly all devices on the market. Software written in OpenCL can run on processor products from all major industries, such as Intel, NVIDIA, IBM, and AMD. OpenCL includes a language to write kernels based on C99, with some restrictions, allowing you to use the hardware available directly in the same way as CUDA C Fortran or CUDA. OpenCL provides functions to run highly parallel and synchronization primitives such as indicators for regions of memory and control mechanisms for the different platforms of execution. The portability of OpenCL programs, however, is limited to the ability to run the same code on different devices, and this ensures that the performance is equally reliable. To get the best performance possible, it's fundamental that you refer to the execution platform, optimizing the code based on the characteristics of the device. In the videos which follow, we'll examine the Python implementation of OpenCL called PyOpenCL. PyOpenCL is to OpenCL what PyCUDA is to CUDA, a Python wrapper to those GPU platforms. PyOpenCL can run alternatively on both NVIDIA and the AMD GPU card. It's developed and maintained by Andreas Glockner. Installing PyOpenCL on Windows is easy when using the binary package provided by Christoph Golk. His webpage contains Windows binary installers for the most recent versions of hundreds of Python packages. It's of invaluable help for those Python users that use Windows. With these instructions, you'll build a 32-bit PyOpenCL library for a Python 2.7 distro on a Windows 7 machine with an NVIDIA GPU card. Go to this link and download the file from here, and the relative dependencies if required. Download and install the Win32 OpenCL driver from Intel from this link. Finally, install the PyOpenCL file from command prompt with the command as shown. In this first example, we verify that the PyOpenCL environment is correctly installed. So, a simple script that can enumerate all major hardware features using the OpenCL library is presented as this. The code is very simple. In the first line, we import the PyOpenCL module. Then, the platform.getDevices method is used to get a list of devices. For each device, the set of its main features are printed on the screen. 1. The device name and device type. 2. Maximum clock speed. 3. Compute units. And 4. Local memory, constant memory, and global memory. Let's run the code now. Open the command prompt and type this command. As you can see, the output shows the main characteristics of the CPU and GPU card that is installed. Wonderful! This video showed us how to use the PyOpenCL module. In our next video, we'll see how to build a PyOpenCL application. Welcome to the 10th video, Building a PyOpenCL application. In the previous video, we saw how to use the PyOpenCL module. In this video, we'll see how to execute the parallel sum of two vectors. As far as programming with PyCUDA, the first step is to build a program for PyOpenCL is the encoding of the host application. In fact, it's performed on the host computer, typically the user's PC, and then it dispatches the kernel application on the connected devices, or GPU cards. The host application must contain 5 data structures. 1. Device. This identifies the hardware where the kernel code must be executed. A PyOpenCL application can be executed on CPU and GPU cards, but also in embedded devices, such as a field programmable gate array, or a FPGA. 2. Program. This is a group of kernels. A program selects the kernel that must be executed on the device. 3. Kernel. This is the code to be executed on the device. A kernel is essentially a C-like function that enables it to be compiled for execution on any device that supports OpenCL drivers. A kernel is the only way the host can call a function that will run on a device. When the host invokes a kernel, many work items start running on the device. Each work item runs the code of the kernel, but it works on a different part of the dataset. 4. Command queue. Here, each device receives kernels through this data structure. A command queue orders the execution of kernels on the device. 5. Context. This is a group of devices. A context allows devices to receive kernels and transfer data. This figure shows how these data structures can work in a host application. Note that a program can contain multiple functions to be executed on the device, and each kernel encapsulates only a single function from the program. In this example, we show you the basic steps to build a PyOpenCL program. The task here is to execute the parallel sum of two vectors. In order to maintain a readable output, let's consider two vectors, each from the 100 elements. The resulting vector will be for each ith element, which is the sum of the ith element vector A and vector B. Of course, to be able to appreciate the parallel execution of this code, you can also increase some orders whose magnitude is of the size of vector dimension input. In the first line of code after the required module import, we defined the input vectors as shown here. Each vector contains 100 integer items that are randomly selected through the numpy function. Then we must select the device to run the kernel code. To do this, we must first select the platform using the PyOpenCL's getPlatform statement. This platform, as you can see from the output, corresponds to the NVIDIA CUDA platform. Then we must select the device using the platform's getDevice method. In the code shown, the context and queue are defined. PyOpenCL provides the method context, or device selected, and queue, or context selected. To perform the computation in the device, the input vector must be transferred to the device's memory. So, two input buffers in the device memory must be created using this code. Also, we prepare the buffer for the resulting vector. Finally, the core of the script, that is, the kernel code, is defined inside the program. The kernel's name is vector sum, while the parameter list defines the data types of the input arguments, or vectors of integers, and output data type, a vector of the integer. In the body of the kernel function, the sum of two vectors is defined as follows. 1. Initialize the vector index using this. 2. Sum up the vector's components using this. In OpenCL and PyOpenCL, buffers are attached to a context and are only moved to a device once the buffer is used on that device. Finally, we execute vector sum in the device using this code. To visualize the result, an empty vector is built with the help of this code. Then the result is copied into this vector. Finally, the results are displayed as shown. To check the result, we use the assert statement. It tests the result and triggers an error if the condition is false. Let's run the code now. Fire up your command prompt and navigate to the working directory. Run the Python file using this command. The output from command prompt should be like this. It shows vector length is 100, input vector A and B is shown, and you'll see output vector result, which is addition of A and B. Awesome! So in this video, we saw how to build a PyOpenCL application. In our next video, we'll see how to evaluate element-wise expressions with PyOpenCL. In our previous video, we saw how to build a PyOpenCL application. This is the 11th video, evaluating element-wise expressions with PyOpenCL. In this video, we'll see how to add two integer vectors of 100 elements using element-wise kernel class. Similar to PyCUDA, PyOpenCL provides the functionality in the PyOpenCL.elementWise class that allows us to evaluate the complicated expressions in a single computational pass. The method that realized this is as shown. Here, context. This is the device or the group of devices on which the element-wise operation will be executed. Argument. This is a C-like argument list of all the parameters involved in the computation. Operation. This is a string that represents the operation that is to be performed on the argument list. Name. This is the kernel name associated with element-wise kernel. Operational parameters. These are not important for this video. In this example, we'll again consider the task of adding two integer vectors of 100 elements. The achievement, of course, changes because we use the element-wise kernel class as shown. In the first line of the script, we import all the requested modules. To initialize the context, we use the cl.createSumContext method. It asks the user which context must be used to perform the calculation. Choose these platforms. Then we instantiate the queue that will receive element-wise kernel using this code. The input vectors in the result vector are instantiated with the help of these lines of code. The input vectors, vector A and vector B, are integer vectors of random values that are obtained using the numpy's random.radInt function. The inputs vectors are defined and copied into the device using the pyopenCL statement as shown. Finally, the element-wise kernel object is created using this code. In this code, 1. All the arguments are in the form of a string formatted as a C argument list. They are all integers. 2. A snippet of C carries out the operation, which is the sum of the vector components. 3. The function's name is used to compile the kernel. Then we can call the element-wise sum function with the arguments defined previously. The example ends by printing the input vectors and the result is obtained as shown. Let's run the code now. Open the command prompt and run the Python file using this command. Select the platform here. The output of this code is as shown. Great! In this video, we evaluated element-wise expressions with pyopenCL. In the next video, we'll test the GPU application with pyopenCL. Here's the final video of this section, testing your GPU application with pyopenCL. In the previous video, we evaluated element-wise expressions with pyopenCL. In this video, we'll first evaluate the kernel call and GPU time. Further, we'll see how to call the testing function and print device info method. In this section, we comparatively tested the performance between a CPU and GPU. Before you begin the study of the performance of algorithms, it's important to keep in mind that the platform of execution on which the tests were conducted. In fact, the specific characteristics of these systems interfere with the computational time, and they represent an aspect of primary importance. To perform the tests, we use the following machines. 1. GPU, GeForce GT240. 2. CPU, Intel Core 2 Duo 2.33 GHz. 3. RAM, DDR2 4GB. In this test, the computation time of a simple mathematical operation, that is, the sum of two vectors with elements expressed in a floating point, will be evaluated and compared. To make a comparison, the same operation was implemented in two separate functions. The first one uses only the CPU, while the second is written using pyopenCL and makes use of the GPU for calculation. The test is performed on vectors of a dimension equal to 10,000 elements. This is the code which we have used here. The test consists of two parts, the code that runs on the CPU and the code that runs on the GPU. Both were taken to the execution time. Regarding the test on the CPU, the test CPU vector sum function has been implemented. It consists of two loops on 10,000 vectors elements. The sum operation of the ith vector components is executed 1 billion times, and it'll be computationally expensive. The total CPU time will have this difference. To test the GPU time, we implemented the regular definition schema of an application for pyopenCL. 1. We established the definition of the device in context. 2. We set up the queue for the execution. 3. We created memory areas to perform the computation on the device. 3 buffers defined as A buffer, B buffer, and C buffer. 4. We built the kernel. 5. We evaluated the kernel call and GPU time using this code. Here, GPU time equals GPU end time minus GPU start time. Finally, in the main program, we call the testing function and print device info method that we defined previously. To check the result, we use the assert statement that verifies the result and triggers an error if the condition is false. Open the command prompt and run the code as shown. The output of the test is as shown, where the device information with the execution time is printed out. Even if the test is not computationally expansive, it provides useful indications of the potential of a GPU card. Awesome! In this final video, we saw how to test GPU application with PyOpenCL. Here we are at the end of this section in the course. In this section, we saw how to use the PyCUDA module. We also saw how to build a PyCUDA application and understand the PyCUDA memory model with matrix manipulation. Further, we studied kernel invocations with GPU array and evaluated element-wise expressions with PyCUDA. We moved on to understand the MapReduce operation with PyCUDA. Later, we also performed GPU programming and used GPU-accelerated libraries with NumPy Pro. Later, we saw how to use the PyOpenCL module and to build a PyOpenCL application. In the end, we evaluated element-wise expressions. I really hope you enjoyed learning from this course as much as I have in creating it. I wish you all the best luck.